Advanced Sciences, who is going to chair the session. And I request her to introduce the speaker, and we'll start the session now. Over to Dr. Anuradha.
Thank you, sir. Very good afternoon, all of you. It's a great honor and pleasure to chair this session. I invite Professor Fikret Yildiz for this virtual conference conducted by VIT Physics Department. Thank you, sir, for accepting our request, and it's so great to see you here, sir. Professor Fikret Yildiz is a professor currently at GETS Technological University. He received his BSc in Physics Engineering from Hacettepe University and his PhD in Physics from GETS Institute of Technology. He worked at Pohang University of Science and Technology in South Korea for 2 years after completing his PhD, and then later he shifted to Max Planck Institute of Microstructure Physics in Germany. He was there for 4 years as postdoctoral researcher. His research focuses mainly on magnetic materials, surface science, functional nanomaterials, thin films for technological applications. Presently, Professor Fikret, he is the Director of Science and Technology Research Center in GTU. On behalf of the organizing committee, we welcome you, sir, for this talk related to synchrotron radiation. Over to Professor Fikret Yildiz. Sir, please.
Hello, everybody. Thank you for presenting me. I would like to thank to all organizing committee, and it's really good online conference. I have to say that I should confess that it's much better than my expectation. Many participants are continuously following, so it's also excite me. So many scientists are going to listen to me. And also I would like to thank to Ramesh Tamankar, who always encouraged me to join this nice conference. My talk is going to be on element-specific magnetic properties of metallic thin films based on using electron radiation. Before starting that, I would like to why I cannot change my presentation. Okay, I want to tell where I am now and introduce my institute a little bit. Gebze Technical University is in Turkey, very near to Istanbul border actually. If we look at here, it's like center of birth, yeah, right? In Turkey, if we center of Turkey.
Professor Fikret?
Yeah?
You are not sharing your slide.
Really? Just a second. I thought I was sharing.
Yeah,
just
please.
A second. Why?
Just come out.
Yes, now it's okay. Yeah.
Now is okay?
Yes. Thank you.
Okay. From here, I passed here. Okay. So I'm working here. If we look a little bit more, it's here is Istanbul, and can you see my mouse on the line? I don't know whether it's visible.
Yes, sir.
Okay.
Black color icon.
Okay, good. Here is Istanbul. It's just beside Istanbul. It's nice place, and this is my research team in Gebze Technical University. We are working on nanomaterials, spintronics, magnonics, and doing research as a team. This is our thin film facility, huge cluster system we have, and 3 different kind of thin film deposition is available here. Sputter system we have with 6 different targets we can use. Pulse laser deposition system, also many targets we can introduce the chamber, and MBE. MBE plus we have some characterization facilities inside the system, like XPS, Auger electron spectroscopy, low electron energy diffraction, read, and STM. Also, we have possibility to use cryogenic system during measurement of particularly STM and some other measurements. Also, we have in situ mock system included this system. I didn't write here. This kind of things they are using in our house. And in the case you need any cooperation, we are always very welcome. What else we have in our house laboratories? We have clean room with optical lithography, and mainly we are using ESR spectrometer for magnetic characterization, measuring ESR and ferromagnetic resonance. Also, we have some transport measurement system, including ex situ MOG here. And for structural characterization, we always use XRD. VSM measurement, we have PPMS up to 8 Tesla, and several Kelvin we can decrease. We have also microwave laboratories from several gigahertz to up to 50 gigahertz. A network analyzer we have, and another mock laboratories we are able to use. And before starting my subject, shortly I want to mention origin of magnetism or magnesia. Everybody knows it's written in lecture book. Nevertheless, I would like to remind again, magnetic names comes from magnesia, which is in Turkey now. Here, magnesia, today we call it Manisa. So first magnetic materials observed here, and that's why magnesia turned to magnetic nowadays. And if you look at magnetic materials technologies, you can see you can add many things. I wrote some of them. Many other technologies can be added to the list. Therefore, big industrial and economical issue investigating on magnetic materials, and also scientific curiosity, another issue to investigate. So we are doing magnetic thin films related on this. Before talking about scientific studies in synchrotron, I want to mention something about what we are doing in our house laboratories. This is pattern thin films. This is soft magnetic material. We use some kind of coffee bean, and for some microwave applications, for magnetics applications, 7 nanometer thick film, and we pattern it and investigate microwave and FMR properties. Another subject we are working, we did some study on spontaneous exchange bias study we performed. In this case, on silicon, we deposited nickel manganese, which is antiferromagnet, and on top of it, after adding cobalt, of course, on silicon, natural oxidized silicon substrate, first of all, we add platinum, and then nickel manganese, and then cobalt. In this system, we observed quite big spontaneous exchange bias effect without any thermal heating. And after doing thermal heating, we observe almost same exchange bias. Another issue what we are doing is magnetic scarmium, another hot subject recently. Scarmium, as you know, it's micron or submicron size, particle-like magnetic configuration. In the center is opposite to magnetic applied field, and around it is parallel to applied field, such a quasi-particle, we can call it. It's proposed by Tony Scarmi in 1960s. And if we look at origin of scarmium, there are 4 physical origin, like Doroshevsky-Mori interaction versus ferromagnetic exchange interaction can create scarmium, or magnetic dipole interaction versus easy axis anisotropy, frustrated exchange interaction, four-ring exchange interaction. If we look at them carefully, size of scarmium in these two interaction create micron or sub-micron level scarmiums, and these two are atomically small scarmium you can create. So we investigated, of course, this one, micron scale. We did some calculations by using MUMAX. These are some other applications reported by other researchers. In our case, what we did, we used MUMAX software and suggested some system. First, we start with this structure. If we apply here one pulse or one DC signal, we create scarmium, and then in this way, it's turned to domain wall, and then finally, again, by passing this narrow part, it's again creating scarmium. Nevertheless, this is nothing interesting here, but if we add this one, a notch here, once you create one scarmium, and after that you apply DC current, then continuously you are getting such a nice scarmiums. It's kind of scarmium generation triggered by DC signal. This excited us. And then if we perform some more details, I can show you. If we have without notch, you see it's continue like this. But if you add notch, and we are getting scarmium like this, and we showed that if it is possible to use as racetrack memory, we can write here some signal, and we can read another place. And if you look at the time scale, when we change orientation, or when you create or delete any scarmium, you can see in the time scale, it's possible to use as racetrack memory. Theoretically, we show that. And before our study, there was some work on it, but nevertheless, all of them proposed by pulse for different study. After our study, we showed that DC signal current also can produce scarmium without any pulse application. Recently, we published it in a scientific report. Another issue we performed, scarmium study. In this case, for observing scarmium, we suggest such structure, interlayer coupled structure. This is perpendicular easy axis material here, platinum cobalt, and on top of it non-magnetic spacer layer, and applied deposited one cobalt system here. We performed some mock measurement and so on also for this kind of system, but I will show you only here, only MUMAX calculations. Without applying any magnetic field, without external magnetic field, we observed that just by changing this interaction between two layers, exchange interaction, we can manipulate the size of scarmiums. Another issue we performed recently, and actually a long time ago we start, during my time in MPI Halle, I started this non-collinear structure. Also, we continue here a little bit different way to perform some sensors. In this case, you have 3 layers. One is non-magnetic, and magnetic is axis of 2 magnetic layers are perpendicular each other, relate depending of interlayer coupling, their orientation can be manipulated. And this theoretical paper shows us by increasing the thickness, energy of the interaction is oscillating. And if we have some small energies, depending of angle, we have chance to have we have chance to produce sensor for small magnetic fields. For this purpose, we perform some structure like this: cobalt platinum and cobalt system separated by non-magnetic layer, platinum non-magnetic layer. And we performed FMR measurement and also some GMR measurement we performed. You can see here, if it is too thin, around 3 nanometer, we see it's coupled and only one FMR peak we observed. In the case we increase the thickness between 2 magnetic layers, you can start to have separate the signal, but still they are somehow connected. If you increase more, it's almost no interaction, and we can see different magnetic resonance behavior. Another work we performed in our house, a strain promoted magnetic anisotropy, perpendicular magnetic anisotropy in cobalt rhodium system we observed. Our motivation was for this study. Before that, we have experience from iron rhodium system, which if you distort it, it can be stay. It can keep its tetragonal distortion up to 50, even a higher thickness. So my idea was, okay, let's apply this idea to iron rhodium system so we can stabilize up to very thick thickness and observe their magnetic properties. And we start like in this idea, and after that we change composition and perform XRD. We prepared different samples, 6 different composition, and depending on composition, as you see, or C-axis is changing. Therefore, this is if we go less cobalt, its lattice parameters is larger. When you increase cobalt amount, it's getting smaller. Nevertheless, also XRD peak is getting wider, which say us somehow when you increase your thickness, it's kind of relaxation can happen, as we illustrated here, as we show here. If rhodium rich, relaxation is less and lattice mismatch is less. But if you increase cobalt, of course, cobalt lattice parameters is much smaller than rhodium, and it's showing this kind of relaxation or behavior. After that, if we look at lattice parameters, depending of composition, these stats are showing, and we got laws, this straight line. And this shows us there is some substrate effect. If it is bulk sample, maybe it will be completely following Regard laws, but due to this MgO substrate, lattice parameters from we got now. And we wanted to study magnetic anisotropies of this system, and there are many ways to study. We have these facilities in-house, but we choose ferromagnetic resonance to investigate. Ferromagnetic resonance is very highly sensitive for magnetic anisotropy studies, and allows us to see also interface effects or different layer effects, and you can probe static and dynamic properties. And it gives us also calculate some values of magnetic properties. So we perform it. We did measurements in this machine, and for two different geometry. One geometry, we call it autoplane geometry. In this case, applied field starting from in plane, we rotate towards film normal. And in the other one, always applied field stay in the film plane. And also RF field always like this, as you see in the picture. What we observe here, we observe two different kind of magnetic resonance behavior. One of them is starting from high magnetic field at the beginning. When you rotate sample from sample plane to sample normal, resonant fields getting smaller, and then after that increasing, which means that magnetic axis is perpendicular to the film plane or parallel to the film normal. This signal is very usual for thin films, always thicker films or many magnetic thin films represent this kind of behavior, which means in-plane z-axis. For in-plane z-axis, we performed in-plane geometry measurements, and we observed fourfold magnetic anisotropy, which means that cubic magnetic structure, cubic structurally affected also magnetic anisotropic behaviors. After doing some calculations by using FMR rules, we wrote our in-house code and calculate the magnetic anisotropies. Magnetic anisotropies you can see in the left-hand side. By changing concentration, it's decreasing. And first, this part is positive, here is negative, which means here is when cobalt concentration increase, it turned to in plane. This part is out of plane, as you see here. This part below 40%, around 30%, it's out of plane z-axis, and above that it's in plane z-axis. This was also, to be sure, origin of perpendicular magnetic anisotropy. We performed DFT calculations. This is done by our co-worker from Marmara University, İlhan Yavuz. He is our cooperation. He used VAST code, and in his calculation, what we observed around here between 30 and 40% of cobalt, we have quite good perpendicular magnetic anisotropy, and to see our A ratio changing here, and cobalt concentration changed this way, and here show us we have out of plane z-axis, and C over A ratio is around 1.1, which is very good fit with our lattice mismatch and strain on the films. Here is cobalt concentration versus C over A ratio. And also you can see here Bohr magneton per atom, depending of composition and C/A ratio. This one, if we look cobalt concentration versus Bohr magneton per atom, when we start increasing cobalt concentration, Bohr magneton is increasing, cobalt concentration increasing, and Bohr magneton increasing as expected. But if you look at here, around 50%, there is some diminish here, decreasing, which means that some cobalt, rhodium, cobalt are interacting, and this interaction is kind of super exchange interaction, and it creates some antiferromagnetic ordering between cobalt, rhodium, cobalt system. There are some publications also on this. Some other guys also observed. Also, we observed some other studies. If cobalt, rhodium, cobalt comes together, somehow some antiferromagnetic interaction also possible. What we conclude from this study, rhodium cobalt alloys, we succeed to deposit epitaxial on MgO, and perpendicular magnetic anisotropy observed up to 50 nanometers, which is quite high compared to many metallic system. Bilayer system and most of system only several nanometer thick you can observe PMA, but in our case 50 nanometer we observed. And if we try even thicker, we observed up to some studies, some trying, we also observed even thicker than this, and we are working on it. What else we observed? We calculate Ku and effective magnetization as depending of composition and tetragonal distortion. Okay, I want to skip the others to save time. And other study we did, actually I did when I was working in MPI in Halle. It was a cyclotron study. At that time, there was one theoretical calculation already done in PRB in this calculation, and the theory was suggesting us there is uniaxial magnetic anisotropy in the case of iron cobalt alloy around 60, between 50 and 60%, and C/A ratio above 1.2. If we prepare such sample like this, we can observe PMA, but this is only theoretical calculation. How one can perform this? We thought that it's thin film good way to create such kind of tetragonal distortion, and by checking lattice parameters, we find palladium, iridium, and rhodium are good candidate, could be good candidate to create such kind of strain or distortion. Rhodium was the best. If we calculate C/A ratio for rhodium, it was 1.24, which is very good when we compare to theory. And we perform iron cobalt rhodium on this by changing iron cobalt concentration. From mock measurements, first of all, mock measurements performed, and depending of composition, from out of plane and in plane, changing thickness was defined and put to this graph. If we look at this, around 60%, we have maximum thickness, almost 15 monolayer thick film can show perpendicular easy axis. And if you change composition, it's decreasing, and this side also decreasing. If we look at Burkhardt theory from here, if we take numbers from there, this is from theory. It's or experiment and theory fits very well to each other. So we decided to check cyclotron radiation measurement by using XMCD in BESI. For that, if we look at here, around 6 monolayers thickness, we can observe MCD measurements. We performed MCD measurement in beamline UE 56/2 and applied total yield, total electron yield method. In this kind of measurements, you have your sample and measuring sample current and another reference signal you are having from ring. And by using this tool, you observe your result. If we look at composition dependence of XAS and XMCD, I showed here only for two different composition, 43% of cobalt and 60% of cobalt. These are right and left polarized X-ray. And if we subtract them from each other, we are getting MCD signal here. The geometry was during measurement, X-ray incidence angle was alpha equals 0, directly coming to on sample, and all different composition films was kept as 6 monolayer thick, and thickness was observed by during samples preparation by meat measurements. After that, we evaluate this data, and by using some rules, we calculated orbital and spin magnetic moment. We already know origin of magnetic anisotropy always comes from orbital magnetic moment. This was our idea why we measure MCD, to show that orbital magnetic moment is the origin of magnetic anisotropy. And if we look at spin magnetic moment, almost no changing by composition. But if we look at orbital magnetic moment for each element, cobalt and iron, depending of composition, it's increasing, and then in some point it above 60%, it's decreasing. If we look at our mock measurement result, it's very similar. So we can say that origin of perpendicular magnetic anisotropy or value of magnetic anisotropy is totally comes from orbital magnetic moment. And if we look at ML over MS values, also similar to our mock result. Another measurement we performed, thickness dependence of orbital and spin magnetic moment. In this case, measurements was performed 110 K for iron and cobalt. Depending of thickness, up to 8-9 monolayers, almost no change for cobalt and slightly changing for iron, which means that up to this thickness, C over A ratio kept constant. But if you keep increasing the thickness of the film, it's starting relaxation, and then orbital magnetic moment is decreasing. If we look at spin magnetic moment decreasing by the thickness, which is tell us there is some spin magnetic moment coming from interface. When you increase the film thickness, this interface effect is decreasing, and this interface effect is actually coming from interaction between rhodium atoms and cobalt atoms. If we conclude the result, iron cobalt alloy films can be grown epitaxially on rhodium 001, and strongly perpendicular magnetic anisotropy is found, which depends on composition. Maximum value of orbital moment was found at the x 0.5 and 0.6 composition in agreement with theory. Another conclusion is spin magnetic moment increases with decreasing thickness due to increased magnetization in the iron cobalt rhodium interface. Another cyclotron study I want to tell here. I did this study when I am back to Turkey by cooperation with Ahmet Akın Ünal. He was working at BESI at that time. It was our cooperation result. And you know, iron rhodium thin films has first order metamagnetic phase transition around 360 Kelvin magnetic from antiferromagnetic ordering to ferromagnetic ordering, fast changing. We want to prepare such sample on NGO, rhodium iron, and by applying, this is our in-house measurement. If we change temperature from room temperature to up to 400 Kelvin, we observed magnetization, as you see, around 360. It's from antiferromagnetic state switch to ferromagnetic, and there is some temperature hysteresis. When you go back, it's following another path and decreasing magnetization, and again switch to antiferromagnetic state. This kind of material can be used for heat assisted magnetic data storage or some sensor applications. So instead of heating, one can apply pulse laser and locally can heat and register something or use for some sensor application. We wanted to show it by MCD measurement, but at the same time, for heating, we applied pulse laser. Our sample holder was, backside was open and let us to introduce laser beam from backside. This is the laser beam, here you can see. And on top of it, we have thin films. We used MgO substrate, both sides polished MgO substrate, because laser was applied from backside of the substrate. When we perform temperature to the sample, this is room temperature, and when increasing temperature up to 400 K, from antiferromagnetic state, it starts to change ferromagnetic state, and you can see the domains, two different domains. You can see blue and red, but I don't know why somehow red one is more here. And then if we go up to 400, it's like this. At this point, we applied one pulse external magnetic
Professor?
Yeah.
We can go for another 10 more minutes, then we'll have the question answer session, sir.
Okay, soon I will complete then. Okay.
Yeah. Sorry, thank you.
Okay. Here, after applying external magnetic pulse, we create single domain. This was the structure we applied pulse and X-ray. And then this was for external heating. We hit the sample externally. But after that, okay, we switched to, we saw our sample is working well. And now the idea was doing, as I suggested here, we applied that, and look at here, this is the line profile I will show down, and this is our laser pulse at minus 0.75 nanosecond antiferromagnetic. First pulse we applied and slightly switch to ferromagnetic state. And if you increase more pulse, it's getting more warmer, and at 0.69 nanoseconds, it's quite red and single domain. Then we let the system slightly cool, and during cooling also we observed magnetic domains by MCD beam. And during cooling, ferromagnetic iron ordering again switch to antiferromagnetic state, and finally around 2 nanoseconds, let's say, it's again turned to antiferromagnetic state. During this system, we observed line profile here during heating and cooling, relative changes of line profile. These are, I want to thank to my cooperators in VITC and ex-workers in Max Planck Halle, Marmara University, İlhan Yavuz and his co-workers, and my co-workers in Gebze. Our team is quite big, but some of my students you can see here, these are all my ex-co-workers in MPI Halle. And this is one photo I took several years ago in my campus in Gebze Technical University. I would like to thank to all contributors listening to me and inviting to me. Thank you very much.
Thank you, Professor Fikret Yildiz. Can we have 1 or 2 questions?
Of course.
Yes. Okay, Dr. Ramesh Tamankar. Sir, Ramesh sir, are you there?
Yes, I'm here.
Please, you can
pose
your questions.
Okay. Okay, fine, I'll ask. Dr. Fikret, it's very nice to listen to you. My question is in the case of cobalt rhodium alloy films on MgO, the lattice constant difference is pretty huge. Then
yes.
How do we explain or how do we expect the epitaxial growth up to 50 nanometers with the perpendicular magnetization?
Yeah, it's a good question. First of all, you are right, but it's not fully keep the same lattice constant up to that thickness. It's if we come back to that point. when you increase the film, it's starting relaxation, and this X-ray also, let's say, witness show us it's it's very narrow, this one. It's proof that system is getting relaxing when you increase the system. Also, FMR results say us, depending of line width we observe, lines which are not very narrow. So it's somehow relaxing. Nevertheless, if we look at the theoretical calculations from DFT part, even you change in this range, still, even if it's relaxing, still it can keep perpendicular orientation. And yeah, it's even if lattice mismatch is too high, somehow still keep epitaxial.
Okay.
We succeed up to 70, 80 nanometers. Still keep epitaxy. I didn't increase more than 80 nanometers, but I'm not sure if we increase when it will start to create create other crystal orientation or going polycrystalline orientation. We don't know which thickness goes, but up to 80 nanometers, no problem.
Okay.
You can get epitaxy.
Okay. Okay. Thank you.
Professor, can we have the last question? Can we have one more question, sir?
Yeah, of course, no problem. I can.
Yeah. Okay. Professor Meenakshi Baisare, are you there? The question is, she is asking about the anomalies that you could face, sir, while doing the DC sputtering in thin film preparation, sir.
I couldn't catch the question, sorry.
The differences that we face when we carry out the DC sputtering, no, to prepare the thin film.
Yeah.
How could we achieve that the DC sputtering? That is the question raised.
For which system? I mentioned different thin films. So which one is she asking? Iron cobalt or cobalt?
No. She has posted in general, sir. In general, you can explain for cobalt, sir. Cobalt.
Okay. As far as I understand the question, she is asking how I keep.
Fikret Yildiz. The question was what kind of anomalies encountered during DC sputtering of thin film magnetic materials?
Anomalies?
Yes. So if you use DC sputtering, for example, what are the problems?
Okay. DC sputtering is, it's always creates some extra problem if you are not arranging system well. First of all, if you are using magnetic sputter system, and there is some magnetic field under the targets, somehow affects the system, and most of system shows uniaxial anisotropy in that kind of films. If your films is polycrystalline or amorphous, you can observe some uniaxial anisotropy due to this technique, and you cannot over that issue mostly. If you want to overcome this issue, you have to rotate your substrate. If you rotate it, you can overcome this issue. We have also rotation possibility in our chamber. If you don't want to have any growth-induced anisotropy, we are rotating our substrate and overcome this issue. What else we can do for magnetic sputtering? Of course, sputter system is quite, compared to MBE and PLD, much messy, quite fast it's depositing, and quite fasting, creating also some defects in your system. To do that, you can apply some voltage to your substrate to decrease speed of ions coming from target. We can do that, or you can change distance between target and substrate. This kind of things one can perform, and we do all of them depending of the system we want to grow. Yeah.
Sir, this is Meenakshi Bhaisare, the one who asked the question. If
Okay.
you may allow, sir, is there any kind of arcing issues you encounter during depositions or a peeling off of a film from the substrate?
Just a second, I couldn't catch again because my sound is echo, so I couldn't catch. Can you tell once more?
Yeah, like
I will change
in
my
a sputtering system.
sound. I have to change. Yeah, in a sputtering system, yes.
Yeah, any form of arcing or a peeling off of a film after deposition, have you encountered such kind of issues?
If I can interrupt Ms. Meenakshi,
Yes,
we can write to the speaker all the
Yes.
problems you have faced, and I'm sure he'll be happy to reply to you. Okay?
Yes,
Yeah,
yes.
of course.
Yes.
If you write me, I'm always open for cooperations or any question. All colleagues can connect me. My email address you can see from system, but I will write to the chat place.
I can give it to them, no problem, Professor Vikram.
And I just wrote now. So anybody, if they need any cooperation or any question, always very welcome.
Okay.
Sorry, I couldn't catch your question. Is it written here? I can read.
Yeah. Thank you, Professor. The great work done by you. Just like that, you have talked for more than 50 minutes. Very great. So kind of you, Professor. Thank you so much.
I also thank you for all organizers and contributors and listeners. Thank you very much, and hope to see you face to face one day.
Thank you. James sir? Ramesh sir? So,
On behalf of the organizing committee, we thank the speaker and the chair of the special session of the first session of the second session of today. We thank Dr. Fikret Elris and the chair, Dr. Sianurada, for chairing the session. Thank you, ma'am.
thank you,
Professor.
sir.
Thank you,
Thank you.
Fikret.
Thank you.
Dear participants, the next session, we are going to start in another 5 minutes. And the next speaker will be Professor Gunter Reis. So within 5 minutes, we are going to start the session now. அதான் கம்மி பண்ணிட்டு இருக்கேன் அது.
Rice for the virtual international transdisciplinary conference, which is ongoing at VIT Vellore. On behalf of organizing team of this conference, I warmly welcome you, sir.
Thank you.
Yeah.
Dear participant, welcome for the second talk of the afternoon session. We have with us the chair of today's meeting, Professor Devendra Nath from the School of Mechanical Engineering of VIT. Now I request Professor Devendra Nath to chair the session and conduct the meeting of this session.
Yes, sir. Once again, I'm very happy to invite you all for this wonderful conference. I'm happy to introduce about Dr. Gunter Rice. Professor Rice holds a chair for thin films and nanostructures at Bielefeld University. He is involved in the main activities comprising of preparation of ultra-thin magnetic and oxidic film systems and investigations of their electronic and transport properties, including experiments with nano-patterned samples for applications, prototype devices for sensor system, data storage, logic gate arrays, and biotechnology. Thin film systems and prototype devices for memory, logic, and sensing down to 50 nanometer feature size are also covered by Professor Rice, along with his colleagues at Bielefeld University. He's a recognized academic researcher working in the physics department, BINAS, CSMD, from 1997 to till date. And he also served in IFW Dresden, IBM TJ Watson Research Center, and Regensburg University. So to his credit, he has published 358 publications in pioneered journals, and he received several international and national accolades for his research publications. And he received the total citation of more than 8,800 with a H index of 43. So once again, I welcome you for this virtual conference on behalf of the organizing team, sir.
Yeah, thank you very much for the kind invitation and for the introduction.
Yes,
so I thank, of course, the organizers very much for inviting me to this very good conference. And I would start now with sharing my screen.
Yes, sir. Over to you.
Okay, can you see the screen?
Yes,
Yes,
sir.
we can.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Fine. Okay. Then I will start my talk. So I want to report on some aspects of magnetic tunnel junctions, which means in particular spin caloritronic and thermal properties of the magnetic tunnel junctions. And you may know that tunnel junctions are the central devices for developments like new memories or sensor devices. And as you see, the results I will report here have been put together by a group of many different peoples from different universities. And I marked the most important contributors here in red in the author list. Okay, so when Bielefeld University comes into play, the most frequently asked question, where is that place? And this place is in the north of Germany, as you can see here. So we are roughly between Berlin and Cologne on the other side. In North Germany, and here you see a picture of the university. There's some special thing about that. This is one building, and we have about 30,000 people in this building when it's fully in operation. And my group operates complete systems for thin film deposition, sputtering, MBE, ALD, and so on. We have up to 18 sources in one chamber. We can do co-deposition and device fabrication by lithography, so that we can make devices down to sizes of about 50 nanometer. So that's more or less a technical background for the work. And now going into science, the basics for all the effects I will discuss are buried in the band structure of the metals. And you see here the band structure of simple copper. So here you have the Fermi level, and you see on the left the band structure, and on the right the density of states. And for copper, you have the d bands very well below the Fermi level, and the electronic properties are determined only by the s electrons here. This is very different for magnetic materials. So for cobalt, for example, which is known to be a magnet, you have the d bands of the majority carriers below the Fermi level, but not so much below as for copper. And you have the d bands for the minority carriers above the Fermi level, partly above the Fermi level. And that means because the d bands are carrying the spin, that there is at the Fermi level a spin polarization, which means for cobalt in this image, we would have more electrons down than electrons up at the Fermi level. And this brings us to an important number, that's the spin polarization P, which is the difference between the number of electrons or the density of electrons at the Fermi level with spin up, subtracted the number of electrons with spin down. And if we normalize that to the total number of electrons, we get a number of spin polarization, which can be 0 or up to 100%. And 100% is an actual research topic. Okay, so summarizing that, when we look at the density of states, which is just summing up all states in the band diagram, then you end up with the density of states. We can have materials where we have at the Fermi level a very different number of electrons with spin up and spin down. And that is then reflected in the spin polarization, and it gives, of course, a net magnetization because there is a difference in the spin density. Okay, now coming to the central device, a magnetic tunnel junction. Magnetic tunnel junction consists of two ferromagnetic electrodes, FM1 and FM2, which are separated by a very thin insulating film. And the insulating film is very thin, and the current is running here perpendicular to the film stack, which means practically that there is a lot of lithography necessary to realize such stacks. This insulator is so thin that there is a tunneling transmission probability where you know this formula probably from the basic courses in quantum mechanics. So this is in essentially an exponential decay of the transmission probability with increasing thickness d of the tunnel barrier. And the k and kappas are the wave vectors in the metal and in the barrier. And for ferromagnets, we just have seen that the bands have different energies for the d bands. And that means that for ferromagnets, you have to split this formula for spin up and spin down electrons. And that means that the transmission probability can be very different depending on the orientation of the magnetizations in these film stacks. And it turns out that they are indeed very different, which means that the tunneling resistance is very different for the parallel and antiparallel magnetization state. And in the end, we end up with devices like that. So we use an exchange bias here for ferromagnet 1. This is due to this antiferromagnet. Then we have the free ferromagnet 2 here, where the magnetization can follow an external field. And then we have a thin tunnel barrier from either aluminum oxide or today magnesium oxide. And for this device, we measure in principle the resistance perpendicular to the film stack. This spin polarization I just discussed can be linked with tunneling magnetoresistance. And the link is done by this formula here. This is a simple formula for the tunnel current density, where you see the tunneling probability as a function of energy, the densities of states, and the probability for occupation. So this is the Fermi statistics in this case. And here you have the occupied states in one electrode and the unoccupied states in the other electrode. And in a more general image, you have to calculate the tunneling conductance, which ends up in a derivative of the Fermi function with respect to energy. And then it turns out in the so-called Giulier model that the TMR in percent is given by the product of the spin polarizations P top and P bottom, so of the two electrodes, divided by 1 minus this factor. And when you assume that the spin polarizations would be 1, perfectly spin polarized, then you see that the TMR can be infinite in principle when you have perfect spin polarization. Okay, how do the devices look like? This is a typical device from our laboratories. We have about 200 nanometer size pattern. So this is the stack of the tunneling device. And in a transmission electron microscopy cross section, you see that this MgO tunnel barrier, this bright material here, is quite crystalline. So you have a very nice crystalline fit of the MgO with the cobalt iron of the ferromagnetic electrodes. And that leads to a very good tunneling, which is called coherent tunneling, which means that quantum mechanics, in particular the phase of the wave functions, are preserved during the tunneling event. Okay, and then when you then come to the basic property and you measure the resistance of this device as a function of the applied magnetic field, you have a steep change of the resistance due to the magnetization of the free electrode around 0 field. And then at larger fields, you see the exchange biased electrode, and the resistance is then small when the two magnetizations are parallel, and the resistance is large when the two magnetizations are antiparallel. And you see something special because this change of the resistance is very high. It's much higher than any magnetoresistance of most materials, and therefore the applications of such systems was driven forward very intensively in the last years. And when you restrict the magnetic field to the range around this steep increase due to the free electrode switching, then you see a so-called minor loop where you have the resistance as a function of the field just running like the hysteresis of the soft magnetic electrode. And in this device, you can, for example, store information. So you can call the upper state logic 1, the lower state logic 0, and then you have the possibility to store 1 bit. And when we look at the development of this MR ratio, so the size of the TMR effect as a function of time, you see that we are now at numbers of some 100%. At low temperatures, the record value is about 2000%. So this can be a very large effect, which is interesting for applications. For my talk now, I have to introduce a second property. This is the Seebeck effect. In a simple picture, the Seebeck effect describes the voltage which is generated in a material when you have a temperature gradient applied to the material. The usual explanation you hear in the introductory courses of physics is that at the hot end of the material we have many fast electrodes. At the slow end we have only slow. At the cold end we have slow electrons, and that leads to an increase of the electron density at the cold end, which means that the electric field would point from the hot end to the hot end to the cold end. Yes, this explanation is not really correct. When we have a closer look and look at the density of states, which is schematically shown here, increase of temperature means that we put electrons from below the Fermi level to above the Fermi level, then the density, the arrangement of the electrons will depend on the symmetry of this density of states around the Fermi level. And if the symmetry is like that, this means we have less free states than occupied states, free states above the Fermi level, occupied below. This means we will get a negative voltage at the hot end. And if the symmetry is different, like in the example on the right side, we will have a negative voltage at the cold end. So in the end, the Seebeck effect depends on the symmetry of the density of states around the Fermi level, while the conductivity depends only on the value of the density of states at the Fermi level. So these two properties are related, but they are not the same. Okay, now what happens when we introduce a temperature gradient in a tunnel junction? Then we have on the hot side, the electrode is hot, which means that the occupation of the states is smeared out due to the high temperature. And on the cold side, ferromagnetic electrode is cold, which means that the occupation is not so much smeared out as in the hot magnet. And that means that when we apply a temperature gradient, we will drive a spin polarized current from the hot side to the cold side. Again, depending on the symmetry of the density of states, the direction can be also different. So we expect to have a Seebeck current here, and when we make an open circuit, we will be able to measure a Seebeck voltage if we apply a temperature gradient across such a tunnel junction. But if we look closer into the definition of the Seebeck coefficient, I again here have the conductance with the transmission probability and the derivative of the Fermi function. And if we calculate the Seebeck coefficient, we see something different appearing, this factor energy minus electrochemical potential. And this mirrors the fact that the Seebeck voltage depends on the symmetry of the density of states around the Fermi level. So then in this image, if we take the two electrodes of the magnetic tunnel junctions, the thermal voltage will depend on the magnetization directions, which means that the Seebeck coefficient for parallel state will be different from the Seebeck coefficient in the antiparallel state. And this effect was predicted theoretically in 2011 and experimentally proven with samples from our group, but with a laser heating and with a Joule heating by these different groups in in Braunschweig and in Greifswald. But it turns out that the size and the sign of the tunneling magneto-Seebeck effect can be very different from the tunneling magneto-resistance due to this factor here in the definition of the Seebeck coefficient. There's also some experimental issue which I just want to discuss briefly. When we make the experiments, for example, here on top of a silicon oxide wafer, of a silicon wafer, then the silicon has some conductance. And then we will see when we, for example, pulse, when we apply laser pulses, you see spikes here in the Seebeck voltage of this device. And these spikes are due to the currents which are introduced in the silicon. And so for if we use only short pulses for heating, which is necessary to measure this effect, this requires that we use either completely insulating substrates or that we take into account these spikes here, that they are not really a Seebeck voltage from the sample. Another ingredient is the temperature profile across a magnetic tunnel junction. Here on the left side, you see the thermal conductance of a magnetic tunnel junction as a function of the barrier thickness, so of the thickness of the insulator. And you see that across the tunnel junction, which is this gray shaded area here, we can expect a temperature drop of something like 1 Kelvin, given the laser energies we have used for heating. And this is still not completely resolved question how large the temperature gradient across the tunnel barrier is really, because you do not, or one does not know the real thermal conductance of a thin film oxidic tunneling barrier. But the values are usually such that there is about 1 Kelvin order of magnitude temperature drop across this tunneling barrier. Okay, when we then measure at standard magnetic tunneling elements, cobalt iron boron, MgO cobalt iron boron, this is the standard working horse for magnetic tunnel junctions. We measure the resistance here in gray. This is the tunneling magnetoresistance in gray, and in red you see the Seebeck voltage here, and you see a perfect match of the two properties with respect to the fields. So this is the magnetic property, the switching between two different Seebeck coefficients for parallel and antiparallel state. But the expectation that we would have a large voltage in the antiparallel state and a relatively small voltage in the parallel state is not true. In fact, we have in the Seebeck voltage, in both cases, a small voltage in that case. And the effect size is quite good. It's about 30–40% of the base Seebeck voltage here, 6 microvolt across this tunnel junction. If we now look into the material properties to make this effect larger, there are some materials which could be a very much better choice than cobalt iron boron, and these are in particular half metallic Heusler compounds. We see here the density of states for the spin up and spin down charge carriers in these Heusler alloys here on top, and you see that in this case of the cobalt 2 iron silicon, we have a very large asymmetry of the density of states at the Fermi level. And that would give a good precondition that we obtain also a large Seebeck voltage and a large tunneling magneto-Seebeck effect for these devices. And here is a layer stack. We have grown 2 different layer stacks with here the cobalt iron, the Heusler compound, as a flat film, and then followed by the tunneling junction, or with also patterned Heusler compound here integrated in a tunnel junction. And yeah, the MTJ from top looks like that. So this is heated then by the laser pulses. And if we look for material here, the Heusler compound cobalt-2 iron aluminum, we immediately see that the Seebeck voltage is much larger than for the cobalt iron boron. So we reach values up to some 100 microvolt. And the tunneling magneto-Seebeck effect is about 93%, minus 93%, which is also a very large value. So the expectation that this special band structure gives rise to larger Seebeck effects in these tunnel junctions is correct. We obtain high Seebeck voltages and, of course, a stable switching property of these tunnel junctions. And when we test another Heusler compound, cobalt-2 iron silicon here in that case, we see that the Seebeck voltage even increases. We reach up to about 700 microvolts for 150 milliwatt laser power. And the TMS effect is again relatively large, with minus 83% in that case. So this expectation that if you look for special band structures and you get then a large magneto-Seebeck effect is true. And the search for larger signals is still ongoing, because you could use that also for information storage, because this device has two states depending on being heated or not. And this could be also used, for example, for data storage. Okay. There are reports about tunneling magneto-Seebeck effect by self-heating. So you just push current through the tunnel junction here, and then the tunnel junction is heated due to the Joule heating. And then you could measure Seebeck voltage if you separate the measured voltage into symmetric and antisymmetric part. This reported values for the TMS more than 1000%, but this is probably not true, because if you do really theoretical evaluation of the tunneling curves, you have to take into account that the tunneling barrier is not really rectangular, but it's asymmetric. And this asymmetry of the tunnel barrier will give you give the same effects as if there would be a large tunneling magneto-Seebeck effect. So one has to be quite careful in evaluating this effect, and direct heating from the outside seems to be more reliable than this self-heating approach for measuring the tunneling magneto-Seebeck effect. Okay, and some news that the group in Hamburg, which is a group of Roland Wiesendanger, they have done already atomistic measurements of the magneto-Seebeck effect. So they are famous for scanning tunneling microscopy, and they were able to image on the atomic scale this size of the Seebeck voltage on such samples. And so there is still ongoing research, both in terms of lateral resolution of this effect, as well as of increasing the effect by choosing the correct or the better materials. And then a last report is the magneto-Seebeck effect in perpendicular MTJs. You may know that the magnetic tunnel junctions with very thin cobalt iron boron electrodes have perpendicular magnetization, and also in this case we expect to have a magneto-Seebeck effect, but up to now the experiments have been done only by this self-heating method, and therefore the values reported may be questionable. Nevertheless, these magnetically perpendicular magnetic tunnel junctions are very interesting, because they are in the moment the core device for developing a magnetic random access memory. And therefore I want to have a closer look to these ultra-thin cobalt iron boron spin transfer torque switching tunneling junctions. It is here sketched on the left side. So in that case, the cobalt iron boron layers are very thin. In this example now 1.2 nanometer and 1 nanometer, and the tunnel barrier is between 0.8 nanometer and 2 nanometer thick. So we have a very thin tunneling system, which nevertheless has still a quite nice structure. So here you have a transmission electron microscopy cross section with the MGO being 2 nanometer thick and 0.8 nanometer thick. And you see that the barrier is still in good shape, even in the case of the very thin barriers. When you then push here a current through the device by increasing the voltage, and you measure simultaneously the resistance of the device, you see that you can switch the system, so the soft electrode, you can switch it magnetically by applying a current. This is due to the so-called spin transfer torque effect, which I do not want to discuss in detail in the moment. And you can switch it also back by changing the current direction. So you can write the information in this device by direct current writing, which makes this system a very good candidate for data storage. And we found that you can have a very, very low critical current density for this switching event here, down to in the range of 10 to the power of 5 amps per square centimeter, which is very, very low current density. But when you have a closer look and you measure the tunneling magnetoresistance as a function of the magnetic field for different temperatures, you see that in this example, you have at 50 degrees centigrade still some hysteresis. But at 85 degrees centigrade, the hysteresis vanishes. So this system seems to become paramagnetic or whatever. But when we measure at these temperatures the anisotropy field correctly, it is still above 1 kiloerstat. So one would expect still to have hysteresis, but this is obviously not the case. And this can be further investigated if we measure the current through an MTJ like that, through a magnetic tunnel junction, as a function of time. And an example is given here. So you see that the current fluctuates here between two values, which means that this magnetic tunnel junction switches thermally driven back and forth between the parallel and the antiparallel state. And that is a typical example of superparamagnetism. So we have a superparamagnetic system at this temperature, but still with a strong out-of-plane anisotropy, which means that the tunnel junction is mainly only in the parallel or antiparallel state and switches thermally driven between these two states. And this is quite interesting because such a behavior could be used as a probabilistic bit, for example, in neural networks. So we decided to look closer into this behavior. And we made a setup for following the resistance as a function of time with a relatively good time resolution of in the range of 5 nanoseconds. We have seen that if we make the magnetic tunnel junction smaller than about 150 nanometer in diameter, then we see no intermediate states in the switching behavior between the the parallel state where we have a large current and the antiparallel state where we have a low current due to the increased resistance. And when we now look theoretically in this behavior, one would expect a mean lifetime in the states, which depends exponentially on the energy difference, on the energy barrier which has to be overcome, so which means on the perpendicular magnetic anisotropy in that case. And we have to add the entropy, which gives us an idea about how many ways there are for magnetization switching in this device. And if we then relate the entropy by this well-known formula to the volume of these possible pathways in the phase space, W, then we would up with formulas like that for a simple one-dimensional picture of switching. So these taus are the mean lifetimes in one of the two states. And this depends then exponentially on the energy term and on the temperature. And so we have handles to get more insight. We can change the external magnetic field, which will change this energy barrier. We can change the voltage, which will change both the anisotropy to the voltage-induced anisotropy change. And we have a spin torque term here, which also is driven by the voltage, by the current density. So we have three handles to influence these lifetimes. And if we look in let's say real theory, in a 3D model, we get a bit more complicated formula for these lifetimes in parallel and antiparallel state. This is due to the precession of the magnetization during the switching events. And there's a very good discussion by Coffey and Kalmikov, which was published a couple of years ago in Journal of Applied Physics about this theoretical description of this statistic behavior. If we now start making experiments, we see here on the right side the dependence of the stability times of the dwell times tau for the parallel and the antiparallel state as a function of the external field. And we see that, of course, that the external fields prefers one of the two states because it stabilizes one, in that case, the parallel state, so such that the lifetime in the parallel state increases and the lifetime in the antiparallel state decreases when we apply an external magnetic field. And this is different for different temperatures because the temperature enters, of course, the lifetimes due to the KBT term in the description. And so we have a system which has an energy barrier and which switches here between the parallel and the antiparallel state, and which has distinct lifetimes in these two states that depend, in this example here, on the magnetic field which we apply. And we can do similar by applying a bias voltage. As I mentioned, this will be a little bit more complicated because at the bias voltage, by applying a bias voltage, we are driving a current through the device, which means we have a spin transfer torque. And due to the applied voltage, we have a change of the effective anisotropy due to the orbital reorientation of the contact between the electrode and the tunnel barrier. And this we can see that when we apply a voltage for a very thin barrier, 1.2 nanometer in that case, we have a relatively large effect of the voltage on the lifetimes. Again, the voltage, of course, stabilizes one of the two states due to the spin transfer torque. And when we do the same for a relatively thick barrier, 1.6 nanometer here, the dependence is much weaker, which means that for 1.6 nanometer, we have much less spin torque because at a certain bias voltage, the current density will be much smaller. Whereas the effect of the anisotropy change due to the applied electric field will be about the same because this scales only with the film thickness, whereas the current density scales with the exponential of the film thickness. So we can separate these two effects. For thick MGO, we have only the field effect, and for thin MGO, we have a spin torque and the field effect. Okay, and if we do so, we can evaluate these curves further, and we evaluated which change of the energy is responsible for which change, for this change of the lifetimes tau here. And then you can make a model where you have here the exponential dependence, which is then due to the spin torque, the exponential dependence of this energy change as a function of the barrier thickness, plus a 1 over barrier thickness dependence for the change of the magnetic anisotropy. And then you end up that we get a change of the magnetic anisotropy due to the electric field, which is the voltage divided by the barrier thickness, with a factor of about 30 femtojoules per volt per meter, which is a number which is similar to values which have already been published. So we are quite confident that we are interpreting the data correctly. And when we do all the evaluations for the 3 different MGO thicknesses we have investigated, one can pull out numbers. So this is the anisotropy K. This is the saturation magnetization of the electrodes, and this is the total energy change between the total energy barrier between the 2 states, between the parallel and the antiparallel state. Here you can already see something strange. I said before that we have measured the anisotropy independently, which was about 1,000 kilojoule per cubic meter. And from this evaluation, we get numbers which are much smaller. And this is not yet quite clear, but nevertheless, first good news, when we plot the switching rate, so this is just the thermally induced switching frequency of these superparamagnetic tunnel junctions as a function of the bias voltage or the magnetic field, we see these Gaussian-like curves, and we can shift these Gaussian-like curves by the other parameter. So here we have the bias voltage, and we can shift the curves by a magnetic field. And here we have the magnetic field, and we can shift the curves by the bias voltage. And this is a very important ingredient for creating probabilistic p-bits out of these tunnel junctions for neuromorphic networks. I will come to this point at the end of the talk. There's one issue, as I mentioned, which has to be resolved. We get a much too small magnetic anisotropy. And if we assume that the tau 0 from all these formulas, this tau 0 is usually assumed to be the frequency of the ferromagnetic resonance, so of the basic eigenmode of the magnetization in these devices. This number is for magnetically perpendicular devices in the range of 10 to the minus 10 to 10 to the minus 11 seconds. That would mean that the probability W, or the number of possible pathways for switching, is of the order of 10 to the 10 to 10 to the 20. And this is an extraordinarily large number. So there seems to be something which is not yet fully understood in these devices, in particular concerning the ways these devices are switching between the parallel and the antiparallel state when they are driven thermally by thermal excitations. And this is in the moment work in progress. So we are trying to get new insights in this behavior. Nevertheless, there's also another activity in the moment. There are some very important and basic papers. Mithrai et al. Published this paper in Journal of Applied Physics, and later on also in Nature Communications, I think, with the title "Overcoming Device Unreliability with Continuous Learning in a Population Coding-Based Computing System." And for these computing systems, which I'm not a specialist in, you need such superparamagnetic junctions, which are probabilistic, which provide probabilistic values, which are very similar to the function which is provided by usual neuron in neuronal networks. And then they can be used in such network. And we can, as I have shown you, we can tune the temperature, the magnetic and the electric fields to tune the properties of these devices. And which means we can tune a network of such junctions, which then could be used for calculating things, or for letter recognition, or other purposes. And that's also something which is in the moment ongoing work in our group. Okay, coming to an end, I hope I have you given a flavor of thermal properties of such magnetic tunnel junctions. And I have to thank first all my co-workers in the different laboratories, mainly in Bielefeld, Greifswald, and Braunschweig, but also in Alabama with a group of Arun Gupta and other groups. And of course with Ankur, who is also hosting this meeting here. So there have been important contributions from the group in Greifswald, led by Markus Münzenberg, also a group of Bart van Wees in Groningen in the Netherlands contributed. We are supported from a theory group led by Christian Heiliger, which actually predicted the tunneling magnetoseebeck effect. There are time-resolved experiments in the group of David Cahill going on about how fast this magnetoseebeck effect can be. And we got different supports from the European Union here, from our DFG and from our federal government. And last but not least, I want to draw your attention to a new lab we have just founded a year ago called MaxSense. This is in an initiative called Research Laboratories Microelectronics Germany. And in this laboratory, we are investigating magnetic sensors and trying to make better magnetic sensors, in particular for cars and mobile devices and so on, for the future. And this is an image of the university in the evening. And last but not least, I want to thank all the people watching and listening to my talk. Thank you.
Thank you, Professor Rees, for the excellent talk that you have given on the topic on the spin caloric and thermal properties of magnetic tunnel junction. Really, it's amazing the way you have explained the basic concepts of the tunneling effect, the Seebeck effect, and also the thermal magnetization switching. Really, I mean, you have touched upon the recent topic on the tunneling effects. Really, we are so thankful to you and accepting our invitation, and you are being with us on exactly before time, even before time you were with us. You have given an excellent talk. Really, it's a motivation for the youngsters to do the research in the latest field on the quantum tunneling. Thank you so much. And we wish to ask you some questions that has been posed by the faculty as well as the students. So now we start with the question session now. So the first question is that, what's the typical dimension of the device used for spin Seebeck effect?
The typical dimension for the spin Seebeck effect was in the range of between 1 micron and 5 micron. Mm-hmm. That is mainly due to the reason that these heating elements, so heating by a laser spot, it's hard to focus the laser spot in the systems we had in Greifswald, in the team of Markus Münzenberg. The laser spot was about 2-3 micron of size, and then you should make the device in this range, so maybe a little bit smaller, such that you do not heat the environment too much, because that would introduce effects. You get all the other voltages, all the Seebeck voltages from the wires, which you do not want. And so it's always, the devices are usually about the size of the heating elements.
Okay. The same question, continuation of the question, can we improve the Seebeck voltage by increasing the dimension?
The Seebeck voltage, I do not think so, because this is a material property, and you will get the same Seebeck voltage for either for a small and a large junction. For a large junction, you can get more current, of course. So the current scales with there is another way to measure that. An open circuit, you measure the Seebeck voltage, and in a closed circuit, you can measure the Seebeck current. And the Seebeck current, of course, will scale with the area of the device.
Okay. And the next question posed by the audience is that, what is the thinnest MGO you have used?
We went down to 0.8 nanometer. There are groups which can go down to 0.7 nanometer, I think. This is more a philosophical question, because you have to make a calibration of your system, and if it's surely below 1 nanometer, let's say. One usually this defines that more in the terms of RA, which is the resistance area product of these tunnel junctions. And for the ultra-thin MGO barrier, this resistance area product is about 1 ohm square micron. So for a 1 square micron tunneling barrier, you get 1 ohm. And that's already a very low value. That's something 0.7 nanometer MGO.
Okay. And the next question is that, what is the stoichiometry of the MGO layer? Is it really stoichiometric?
Of the MGO?
Yes.
Yes, it is stoichiometric up to what we can prove, because when we grow very thick layers, we determine the stoichiometry, and this is MGO 1-to-1 within the accuracy of the measurement. So the accuracy we make fluorescence is about 1%. So, but for the very thin layers, it's quite tricky, or it's almost impossible to measure the stoichiometry with this precision. But nevertheless, when the MGO would be non-stoichiometric to a large amount, this would mean that you get a sort of whole conduction of the MGO would become conducting. Mm-hmm. And that would deteriorate this tunneling effect.
Okay.
And so when you have a large tunneling magnetoresistance, you can be quite sure that that the MGO really serves as tunnel barrier and not as conductor.
And what's the background Seebeck voltage you see in the tunnel junction? Is it, say, 6 microvolts, they have asked?
Let me see. We have to go back. Okay, here you can see the background voltage. Let's say this black curve here for the 150 milliwatt heating was about 300 microvolts, which means this is, yeah, one has to separate the effect. This is the Seebeck voltage of the tunnel junctions in the parallel state, plus some possibly, yeah, Seebeck voltages of the wiring. We try to make the wiring as symmetric as possible, such that you do not get Seebeck voltages from these wires. So we have gold from bottom and gold from top, such that the offset Seebeck voltage in that case should be quite small. And you have seen, for example, here, for this example of the cobalt iron boron, the Seebeck voltage was much smaller. And you see here the offset is down to about 6 microvolts. And I would guess the offset, the real offset from the wiring is in the range of 1, 2 microvolt.
The next question posed by the audience is that how much can we reduce the size of a usual hard disk if we use spintronic technology?
Oh, while we are, I'm thinking in 1 bit on the hard disk. This is now in the range of, I think, 50 nanometer. And I guess one can reduce it due to for the reading elements, for the read heads, which are in the moment made from the tunnel junctions. You could reduce it to about 10 nanometer, I think. But there is another issue because the media, so the storage media on the hard disk, is a magnetic thin film system, which has some granularity usually. And you must have enough granules in 1 bit to overcome the statistics of the different granules. And to my knowledge, there are about 10 granules now in 1 bit. And so I think it could be down to something like 10 nanometer, but that's mainly a question of the storage film system on the disk.
Okay. Professor, could you throw some light on the thermal magnetization switching? What are the future applications?
I think the main application is in these probabilistic bits. There are now many groups working on using probabilistic bits, so bits which are behaving statistically, but where the switching rate can be tuned by some external parameter. You can create networks from these bits which work like neuromorphic networks, which could be much more tolerant. For example, if 1 bit fails, they can be repaired. So I think this is a very interesting application. I think there was a Nature paper where they have realized, I think, a network of 8 cells, 8 p-bits, and they made letter recognition. And I think this is a field which could be driven forward because there is a very basic possibility to create really hardware networks. So not software neural networks, but hardware, which could be self-repairing and being much more similar to the brain, which also operates at the thermal limit.
And one more question from the audience. Why NdFeB is not successive material as compared with COFeB as concerned with spintronics?
I did not get the materials.
Oh, yeah, neodymium. Neodymium.
Neodymium.
Yeah.
That is because neodymium is a 4F material. And so the band structure looks very different. And one does not expect a really high tunneling magnetoresistance for example, neodymium-based alloys. So neodymium says the magnetic band is a 4F band, which is very different from the D bands.
Okay.
Yeah, some of these very hard magnetic systems are used for biasing, so for getting the reference electrode.
Fine. Professor Rees, we are so much thankful to you on this wonderful day which we had an interaction with you. I think all the participants would have gained a lot of information from your talk. We are so grateful on behalf of the organizers and all of us here in VIT Vellore. We thank you so much, and we want the future cooperation And also, we thank you so much. You're so wonderful in explaining the basic concepts, which even the students, all of the students would have understood. So thank you very much on behalf of the organizers.
Okay, I thank again for the invitation and wish you an enjoyable conference in the next days.
Yes.
Thank you.
Thank you very much. At this juncture, I would thank the chair of the session, Professor Devendranath from the School of Mechanical Engineering, for kindly accepted our invitation to be the chair. Thank you very much. Thank you one and all. Now we are going to have the next speaker, and may I request Professor R. Vijayaraghavan from the School of Advanced Sciences to chair the session and introduce the speaker. Over to Professor Vijayaraghavan.
Professor James.
Professor Vijayaraghavan sir, over to you for the introduction of the
1
speaker,
minute,
please.
yeah. It's audible.
Yeah, you are audible.
Yeah, I am not hearing you.
Oh,
I am not able to listen. I have some difficulty.
your
with the
voice is
speaker.
audible, sir, perfectly audible.
Yeah, I think. I don't know.
We can
Sir,
hear
you can start, sir.
No, sir.
Vijayaraghavan sir, you can start, please.
Yeah. Sorry, my speakers are not good now. I can upgrade. Okay. So, good evening to the delegates and the speaker. I'm audible there, Dr. James?
Yes, sir, you're perfectly all right.
Yeah. It's my pleasure to be part of this conference, and I thank Professor Rajan Babu and the other committee members for the opportunity. This session is the third talk in the afternoon, is by Professor Satish Krishnamurthy. And before that, a few words to the audience. I think you are familiar with the procedure that you have to ask questions through the chat box. I will collect those questions at the end of the session, 40 minutes. I will ask the questions. So, Satish Krishnamurthy, this is about 45 minutes talk, 40 plus 5 minutes. Okay, it's my pleasure to introduce Satish Krishnamurthy to this audience. And he is currently the chair and the professor of energy technology, the Open University, United Kingdom. He has experience of over 20 years in energy area within the academia and industry. And he has been specializing in the laser and plasma processing of renewable energy materials and chemical vapor deposition of nanomaterials, which are a state-of-art processing technology. And his research is widely published in scientific journals, book chapters, and the impact factor of 8 to 35, over 70 publications, and 8,000 citations. It's really wonderful to have the cited scientists be with us. He's committed to practical applications, and he has been commercializing technologies and strengthening the capacity of entrepreneurs and startups in developing countries. And he has been collaborating with many countries in multidisciplinary areas and multi-collaborations within UK and abroad, and probably in India too, I think. And we look forward to have collaboration. Maybe it's going on, I don't know. And more importantly, which is not mentioned here, is that Satish Krishnamurthy has won an award from the, I think, if I remember correct, Department of Energy, USA, as an upcoming or contributing scientist for energy area. So it's my pleasure to invite Professor Satish Krishnamurthy to deliver his talk in this virtual conference on transdisciplinary approach. Satish Krishnamurthy, please. I think you have to unmute him. I don't know.
Professor Satish, your voice is not audible, please.
You have to accept the unmute.
Yeah, I hope you are able to hear me now.
Yes,
Yeah.
yes, perfectly, perfectly.
So, good afternoon, everyone. And it has been really a good privilege to get myself introduced from Professor Vijay Raghavan. I think my research fascination started in the IIT Madras lab way back in late 90s. And probably Vijay Raghavan is one of the first few people I met to inspire my research work. And I think it's called probably a blessing that I was introduced nicely by Professor Vijay Raghavan. Thank you so much for your introduction. And thank you so much for VIT for organizing this. This is a very important kind of brain circulation and ideas, even in this very tough times when people are undergoing some really challenging times. And just to take our mind off and also to understand what the upcoming technologies are offering to us. So without any further ado, I will share the screen. I hope you can see that anyway. Right, let me continue. Good morning, everyone. And so I would be here talking about engineering of 2D materials for energy and water applications, which are really keen, which are very key for not only current generation, whereas for the future generations as well. So I'm currently working as a chair of energy technology at the Open University in UK. And the right is the cover image of our 2D materials being published in PCCP, where we engineered them for P and N type for solar cell applications. I'll go through all these things in my talk. Let me give you, not many people will be aware, what is this Open University? Is it pretty much, particularly in India itself? Like in India, Open University is the Indira Gandhi Open University. I think, to be honest, this IG Indira Gandhi Open University was started by the Open University under the request from the Indira Gandhi. And this Open University is one of the world's successful distance education university, established way back in late 60s or even early 60s by the British Parliament to give access to education to all. That's the whole motto of this. So currently we host 200,000 students each year, and we have most diverse population in UK today and one of the largest student population we have. And we always believe in enhanced learning through proper delivery. We use many technologies, including postal systems to digital to many other modes and even web modes. Now we have designed remote labs. If you go and see Open Science Lab and Open Engineering Labs, you can see plenty of our research being done, research and also the teaching labs being done through remotely by robots, etc. So it's a fantastic mode of education in this modern world. So without any further ado talking about education, so let's talk more about the materials and our group and what our research does. And I just wanted to mention, OU is the largest provider of higher education in Europe, about close to 20,000 disabled students. We have, that is close to 20,000, that is about more than 10% of our students has some disability. And this is one of the key structures which we proud of, saying that, yeah, we were there for the people who cannot access the education through normal means, education and even research. And that's our group, Nanoscale Engineering. So all the work which I'm presenting is done by the group members, and also I bring funding and others. And then we received some award as UK India Research Excellence Award and many others for our work. And I work on collaborations as well. So because there's no one can do one thing, we need everyone, join hands together. So that's our motto. I'll go through all these things. So sure. So what is very important for me, as Professor Vijay Raghavan was telling, that I was in India and then I progressed well in my career over 20 years. Probably 20 years is a long time in UK. So I've been in UK for 20 years. So having seen both sides of the globe, I came to a realization that research should benefit society. And yeah, publication is important, but publication and perish is not the language we need to use. The publication, process, and prosper, how it benefits the society. So that's why I framed the theme of my research groups as socially oriented transformational research that has direct benefit to society. So all our research projects, which we do on high-end materials, we also publish on high-end journals as well, but our focus is more towards how it will benefit society and goes towards commercialization and industrialization processes. So what we do is we use materials for surface engineering of materials, 2D materials, and any nanomaterials in that case, and functionalizing them with low-cost atmospheric pressure plasma for energy storage, water treatment, even solar fuels, that is getting hydrogen from water, and also not only from water, from the wastewater itself. So I will show you those things in my talk. And we also developed a new type of deposition method called plasma activated, atmospheric pressure plasma activated deposition. So it can deposit onto any surfaces. As you can see in this right image, I'm pretty sure the arrow you can see. In the right image, you can see that the plasma plays a critical part in depositing onto the surfaces. So which we do as well. And we are also working in collaboration with others on sensor technologies, 2D materials for sensor technology, smart sensors, particularly for accidents detection, and then also precaution of accidents, and smart materials coatings for buildings and smart buildings as well. So there is a huge recipe is there. As I mentioned, that our focus is on socially oriented research that has direct benefit to society. And I'm pretty sure most of you are aware of UN Sustainable Development Goals that cut across many themes. So this is I'm always fascinated by strong messages. And this global goal is a very strong message given by the United Nations that anything which stops the development of the nation is there, or anything which needs catalysts to improve the development of the nation, whether it could be any field, is there. So we are working right from no poverty to zero hunger, and many others, no poverty to zero hunger and many others. It cuts across different themes. And our work is primarily, we are not working on all the SDGs. Our work is primarily on quality education, which I'm not going to cover. Gender equality, we do quite a lot of gender equality, but today's I would be talking more on clean sanitation and how the material influences the clean sanitation and water, clean water, affordable energy. So what we do is, as Vijay Raghavan was telling, that we have work on different collaborations with industry and academia. It's very important to understand both sides of the language, what they speak, and how the material influences, material processes, and our transfer of knowledge influences. So we work currently with India, we are working with IIT Hyderabad, IIT Delhi, SRM Institute of Technology, PSG College of Technology, etc. And we work on plasma processing of materials, electrochemical methods, deposition, etc., deposition of various techniques. We also make sure that everything is a low-cost materials, and then using the plasma activated deposition, we create structures. And we create structures, etc. And then we do high-end characterization using XPS, XRD, Raman to understand the surface interfaces, properties, and then devices. We work very closely with industries. Nile Limited is a recent one. We work on recycling of batteries, extracting new materials from the batteries. And Watson Envirotech is it's a wastewater treatment, and then other companies, including Bank of England. Bank of England is who makes notes for currency notes for us, and like pounds, and they are interested in counterfeiting the notes, like what needs to be done, like how we can see the counterfeiting notes by shaking the notes itself, so that if you shake the notes, the color should change. So we are working on how we can incorporate different types of 2D materials into that, so that it can change its color as a function of stress and strain. So these are all very important. Please keep this in mind. you will know why I'm talking this. Okay. Sorry. So our ongoing, but I think Vijay Raghavan was suggesting that I work with, so I'm putting the projects which are funded in India itself. So apart from India, we have projects funded outside as well. These are all current ongoing funded projects on integrated wastewater treatment with PSG College of Technology and a company called Watson, Environtech, and recycling of batteries with IIT Hyderabad and Nile. And then we are working on another recycling battery, which is funded by British Council with IIT Hyderabad and some other company, which I should not mention now. And we are also working on plasma deposition of solar cells, flexible solar cells, which is funded by Royal Society with SRM, and then the industrial wastewater treatment, that is a GCRF, and also European Union projects with one of the partners, India and IIT Delhi as well. So there is a huge things going on, and all these comprises of industry innovation. So we have industry innovation and its environment and also its energy as well. So our clear theme, cross-cutting theme is on this. Okay, it's already 10 minutes. I'll just quickly rush through why I'm fascinated by materials. Materials and engineering of materials fascinates me all the times, because without materials, we are not there. We cannot innovate, we cannot exist. But if we look back also 200, 300, or even 500 years ago, there's still materials there evolved. But I think we are revisiting, like, don't quote me here, we may be even revisiting what we have done before. So foundation of technology is always materials. For example, the copper. Without copper, there is no electronics. I can't even communicate with you now because it forms a huge pillar for electronic industries. And again, the buildings, concrete and skyscrapers. Concrete makes a huge impact on the, so these concretes are nano clays inside, and that acts as a binder to keep this. This is again a materials innovation. And rubber tires for cars. So different types of rubbers. So these are all like materials. How these materials can be made even more powerful, lighter, and environmental friendly. That is where the whole world is moving. And it is the right thing to move because that will fit into the SDGs where using less resources, what is available, right? So a few minutes back, I was telling we may be reinventing the wheel, right? So the reason why I'm saying is this. If this painting is 1965 paintings, it's still it's all gold. It's in gold, and you can see that the color is in the same state as probably it was before. So we don't know why the reason is. I'll come back to. I'll show you in my next slide. The color of the gold changes as the particle changes at the nanometer scale. This is some churches in Europe where you see a stained glass. The stained glass is still like that without changing any color for years. Whereas if you do the painting in our house, it changes every few days. After 5 years, we'll say that, yeah, change the paint again. Why it is? Probably it is due to gold nanoparticles. Yes, they are gold nanoparticles. It is proven they are gold nanoparticles. As you can see that the size of these nanoparticles defines the different colors. And once it is there inside, it will not go out. So it is strong because the smaller the nanoparticles, the strength of the materials is enhanced multiple times. And that is the things. But coming from Tamil Nadu myself, I also feel that there should be something there in Meenakshi Amman temple. So this photo was taken by me. I visited the temple, and this is nothing but the similar gold nanoparticles with different colors. So we are just reinventing the wheel, which we already forgotten centuries ago, and then tailor making it now for different applications. That is my understanding. Right, 2D materials. So we all know probably here, there are many researchers are here who all know what is a nanomaterials is. But just to give a very, very brief, probably 1 or 2 slides, I would spend here is, if all 3 dimensions of the materials are quantized, then it is nanoparticles. So nanoparticles shapes the 3 dimensions. It's a 0-dimensional nanoparticles where all the 3 dimensions are nano-sized. If 2 dimensions are nano-sized, like a wire or a string, if you say that, so this string and then the cavities are nanometers, but the length is not in the nanometer scale, then it is a 1-dimensional nanowires. Whereas for 2Ds, what makes 2Ds interesting, which I will tell you, the 2-dimensional nanoparticles is pretty much like my hand. So where there is only one dimension is constrained, whereas the rest of the dimension is pretty much like a bulk. So that is a piece of paper or a sheet. So that is two-dimensional material. In simple language, anything you see is bulk, and 2D nano sheets, graphene is everyone know, and then one-dimensional nanomaterial. Again, I wanted to stick to the carbon family, carbon nanotube, zero quantum dot, or nanoparticles. How does it affect when you reduce the dimensions? As you can clearly see from this image, this is a sheet. I will go through this as well in my other talks. So you are going from the cage, from the tube, one-dimensional to two-dimensional by slicing it. The slicing the property or reducing the thickness of the material into single atom, it enhances the properties extremely by diffusion, electron diffusions, and also electron mobility, and also the band gap, etc. for different, this is for graphene, but in general for 2D, I will show you in my following talks. So that extremely nice properties, which is not seen in bulk, can be seen in 2D materials. And these 2D materials are earth-abundant materials. It's not that we are working on high TC superconductors or others where you have to spend more money or to get the technology. So as I said, that we need to have a socially oriented research that has direct benefit to society, and these materials can be beneficial as well. So we all know that graphene was the first modern 2D material to be isolated since 2004. I just wanted to tell a couple of stories when I was started doing exactly 2001 to 2004. I did my PhD, and I was working in a synchrotron. In the synchrotron, we used to peel the graphite, the Scotch tape. I'm not joking, taking the graphite flakes because we wanted to deposit some carbon onions and carbon nanomaterials on top of graphite. So we used to do a sticky tape and make sure to cleave the graphene. And we always see the shiny bit, but we never realized that is one that will win the Nobel Prize. And we just put it in the bin. I'm one of those who could not identify what it is there in that particular shiny material. And that particular shiny material was isolated in 2004, and literally hundreds of examples came, and that is a Nobel Prize. So students always pay attention to every single aspect. It's very important that students or anyone to see that serendipity can come at any time and any scale. Okay, in this talk, I would be focusing on graphene, little bit of graphene and modified graphene surfaces. And then another family of 2D materials are hexagonal boron nitride. I will tell you what it is and what exactly makes a difference between hexagonal boron nitride and graphene. TMDCs, that is transition metal dichalcogenides. And then another new material, phosphorine zines, and there are many others are there, even maxine are there. So I'm not going to focus on maxine. That's a huge area. Probably you might have already listened to Yuri Getowski as well. So I don't want to go into that details. But these, and also there is another family, borophene, it has come. So there is lots of different nice 2D materials of research is happening in this stage so that you can activate your mind. Graphene is Graphene is a fascinating material. As you all know, it's optically transparent, but so it absorbs only 2% of incident light, high conductivity, and a single layer of graphene is just atomically thick, 0.3 nanometers, and it has hexagonal structures and hexagonal lastly structures. But what is hexagonal boron nitride? Hexagonal is an isomorph of graphene, very similar crystallographic structures with hexagonal lattice structures, but they have a very, instead of carbon, you change boron and nitrogen, pretty much like this. I don't know the time gap between my slides, whether it's coincides, but I will try to talk slow. The purple atoms are nitrogen and the blue are boron. So I can see that both are pretty much similar, but both are 2D systems. But their electrical properties varies because hexagonal boron nitride is a wide band gap insulator, whereas graphene is a semi-metal. So can we sandwich these two pretty much like a burger to have a different types of properties? Yes, That is another type of research going on, but I'm not going to talk about the heterostructures here. And TMDCs is another type of 2D materials. They have MX2, like M is a molybdenum, and it could be metal, could be molybdenum or tungsten, and X could be sulfur, selenium, or telluride. That how this is different from graphene and others is they are completely different structures, structurally different. TMDCs are van der Waals materials. Van der Waals materials are weak bonded materials, and which each layer of 3 atoms thick in case of chalcogenides, with the metal layer sandwiched. But unlike this hexagonal structure, TMDT takes different, either trigonal symmetry or tetragonal. And most favorable thing is the trigonal symmetry, with particularly 2H phase, and resulting in semiconducting properties of molybdenum sulfide, or in case of a molybdenum selenide as well. Let us compare two different 2D materials, MOS2, TMDCs, particularly MOS2 on the left and the tungsten telluride on the right. So as you can see that MOS2 is commonly found in semiconducting phase. This is unfortunately, I don't have a good marker. So if you see that both are two-dimensional transition metal chalcogenide, with MOS2 is most commonly found in semiconducting 2D phase, whereas WT2 is in 1T phase. But at 1T phase, WT2, that is the tungsten telluride, takes the shape of metallic phase. It's quite amazing to see that how this has changed. Even though structurally it looks different, but the properties changes within the few band gaps. Okay, if any material that is governed by the electronic and optical properties, these electronic and optical properties, if you see that, they are governed by the spaghetti diagram or electronic structures, right? And this describes how electrons, so left is the comparison of bulk MOS2 and the monolayer of MOS2, that is 2D systems, right? The 2D systems. Okay, if you see that how electrons move in the material is a result of its periodicity of the crystal structure. When a material goes from the bulk to the 2D systems, the periodicity is removed. And when the periodicity is removed, the direction perpendicular to the plane, that results in the that results in the change in the band gap structure. So the materials goes from extremely high conducting phase in case of graphene, and then here, particularly in the monolayer of MOS2, it goes into fluorescence of MOS2. So from graphite to graphene, it goes into high conducting, whereas from the MOS2, it goes from the semiconducting phase to highly fluorescent phase. This is amazing things which is used for different applications, including whole transport system for solar cells and other medical applications. I will touch about phosphorin. Phosphorin is another single layer of materials. It's a black phosphorus. That's what they call these days. It's a fantastic material. This particularly, you can tune by the band gap of this material by stacking arrangements, different stacking layers. And phosphorin is amazingly useful for optoelectronic applications because of tuning of the band gap and the coagulated structures. And the other family is xenes. So these are all xenes. Xenes is nothing but we can extract 2D materials from silicon. So whereas graphite, you do the mechanical exfoliation. Whereas in the case of xenes, particularly the silicene, germanium, tin, stannine, all these are epitaxially grown. So either you etch the material or you try to use physical vapor deposition to extract the material, or use some catalyst to take the few layers out of this system. So these are all fantastic hexagonal materials similar to graphene, but they are buckled to very varying degrees. Unlike graphene, they cannot be exfoliated, as I said, from the bulk, but can be epitaxially grown. But this generally very strong interaction between the substrates, so they're amazingly stable, but still they are all infancy in their things. But you can see from the structures here, the property depends on how the structural orientation and the bond length. So this is all plays a huge parameters. This is flat and sometimes with its angle. So this is a very interesting class of materials to explore. I wanted to show only a few. I don't want to spend more time on this, but this is very interesting to know, particularly for the students who are aspiring to do this 2D materials. If I take diamond, say for example, you can do mechanical exfoliation of diamond. However, the diamond have a chemical bonds oriented in 3 dimension. So if I start thinning down, slicing down the diamond by cutting these bonds, then that will leave this red marks are nothing but the dangling bonds, okay, which are chemically and energetically unstable and can force the material to rearrange the structures to its lowest surface energy. Okay, so if you can do the cleaving, that's why when you cleave the diamond, the nano diamonds, you get it into different type of structures like onion-like carbon, or some nano diamond still will be inside, and then that will be covered by the 8-membered link because of the holding dangling bonds. But if you look at the right, another allotrope of carbon is graphite, has a strong chemical bonds, okay, only along the planes, so that's stacked on top of each other by weak van der Waals interaction. When you have a weak van der Waals interactions, when you started doing mechanical cleaving, there leave no dangling bond and you will get a good crystal structures. Okay, so it is pretty much like this. You scotch tapes, and then this publication is by us in the Nature, which was already, I think, cited by 5,000 times or 6,000 times maybe. We talk about how we exfoliate graphene from the graphite. So it's a liquid exfoliation. You can, this is now in the powder form you take, and then you start putting either some reactive solvents, or even nowadays you can even use a surfactant. The reactive solvents, if you have, creates kind of hydrogen bubbles, you can see these bubbles will go and penetrate onto the surface, and then they help to lift off the layers of the graphene. This is one of the publications in Nature which we did. Right, let us look at the publication. So why it is all interesting? Why the community? The community is interesting because it has fascinating properties. So I covered from 1990s till 2019. So of course everyone knows in the scientific field that graphene is 150,000, or I think this 15,000 publications. Then the phosphorin is slowly picking up. So you are not still in the, there is a lot to explore, but it is still kind of unstable. And there are still a lot to explore. And then boron nitride, it's coming up again. And MOS2 is picking up. MOS2 has different structures. You can start doing composites of MOS2 with another oxides to have different fascinating properties. Tungsten sulfide, germanium, and look at that guy. This is very important, borophene. I think borophene will be another amazing 2D material which will be explored in future. And similarly, why all these 2D materials needs to be explored? Because of their fascinating band gap and tuning the band gap. We can easily tune the band gap depending on the bond length and work towards the change the properties or have different heterostructures. Right. This is one of our publications which comes as a cover image. We engineered the graphene oxide from P to N type using low power atmospheric pressure plasma jet, and where we introduce nitrogen dopant, and these nitrogen dopant will change the properties. I will show you how. So left is the X-ray photoelectron spectroscopy, where we use pretty much, if you can see that this is a plasma source which we are using, and we can pretty much functionalize in situ, okay, without any chemical, because we don't want to use chemical methods to do the changes. We wanted to make sure that the environmental waste is another thing, and also it takes a long time to do the chemical reactions as well. You need to undergo different properties. This is a one-step reactions where we functionalize in situ the in plasma the graphene oxide, and then we change the chemical and mechanical properties, and we study the electronic properties. As you can clearly see the changes. This is a nitrogen 1s binding energy, and you can clearly see that the chemically bonded nitrogen grows, and then after that it dies. So this is a pyridinic and graphitic carbon, and how this influences the work function of graphene is a fantastic thing. So you can clearly see that within 10 seconds, we are talking about seconds here of the growth. Within 10 seconds, we are able to change the work function and the surface potential of the material when we use a low power atmospheric pressure plasma. when we do that, we can clearly see that the changes in the aromaticity or aliphaticity of the carbon-nitrogen bonds, and how these carbon-nitrogen bonds both changes the pi orbitals of carbon-nitrogen and also sigma orbitals. So these really influences the conductivity of the system, and also the it's already 30 minutes, and also the properties of the material. And we did the calculations, and you can, sorry. Yeah, so we did the right is the X-ray NEXAPS, that is NEXAPS is near edge X-ray absorption spectroscopy, where you can get more information on the local carbon chemistry. That's, for example, 1s transition, because when I started putting the nitrogen onto the system, I would like to know what is happening to the carbon and the nearest neighbors. So how it influences. So we did the NEXAPS, near edge X-ray absorption fine structures, and we were able to see a band shift towards lower energy, and that is resulted in different types of P-type and N-type bonding. Sorry again. So as you can clearly see that the graphene exposed by the really low power plasma, and the peak at 291, that is in case of the right, the binding energy corresponds to the sp2 lattice, and the presence of graphitic nitrogen is more disruptive, which I showed in the previous graph as well, how the nitrogen evolution happens. And then the blue shift is in the carbon, as you can clearly see in the third figure, the carbon is blue shifted. I don't know why it's timed, is it? Carbon is shifted towards the blue by increasing the charge density and the charge carriers, which pretty much what I was introduced at the beginning, how 2D materials in the systems, how when you change the structure where the nitrogen atom sits, you can change the electronic properties. That's what pretty much is happening. And we also observed the similar in Raman. And how do we use this? We are currently working on perovskite solar cells and organic solar cells. So what we are trying to do is this structure already been made. So we are having MAPB structures, and inside the MAPB we put graphene oxide and also our functionalized system, and we are seeing a huge increase in the efficiency. That is particularly important, and also increases stability, because there's a whole transport. Probably we use pyrometad. Now what we are thinking is we will functionalize. If you see that we have wanted to functionalize pyrometad along with graphene and print it, and then see the structural dependence. So this is getting really, the efficiency of our systems is about close to 10 to 12% now, probably because we are still in optimizing the stage. Then I will quickly go into transition metal chalcogenides, which we are using, and from the bulk systems to nano. So we are using pretty much like a hydrothermal method, very simple hydrothermal methods to do mass 2 bundles. And we use titania as a photocatalytic material along with mass 2 to create heterostructures, and then use it. I will tell you how it will be using for dye degradation, etc. So the big picture of the societal challenges, this is a project funded by Royal Academy of Engineering and also European Union as well. And on textile industry, India is one of the major exporter of textile. It's about $60 billion maybe in 2019, but dyeing is one of the most polluting things. I myself visited quite a few industries close to, not far from Vellore. I think Perundurai is one of the areas which I went on, KG denim factories and many other things are there. So I visited, and then I was able to have an NDA with them. There are quite a lot of things which we did, and now currently a prototype is sitting in one of the industries on our photocatalytic reactors, photo and electrocatalytic reactors. So these dyes are currently carcinogenic compounds. It's still leaving, and then the maintenance of these effluent plants itself is a challenge. So this is what I found, and then to address this, we thought that there could be some smaller compatible way to address. So photocatalytic work, which we are working with Open University, we work with different oxide systems. So I don't want to go into the details. So we are working on pristine TiO2 and then also hydrogenated TiO2 and the composites. This is a mass 2 one. So we also work with mass 2 layers and integrating mass 2 into TiO2 systems. And also we work on one-dimensional nanowires as well. So incorporating one-dimensional nanowires into 2D systems. Okay, so that is where we are working on. If you wanted to know, very brief introduction of photocatalytic process is initiated by the generation of, you have electron hole pair, as you can clearly see there. You create electron hole pair within the semiconductor upon absorption of sun or a photon. And then on the catalytic surfaces, these photo-generated electrons and the holes react with the dissolved oxygen, which is there in the surface, and then producing radicals. And it is also possible to generate photo-generated holes at a catalytic surface, able to directly oxidize the organic compounds, which are carcinogenic in this case, and then making into anions. So this is what pretty much covers. And I think I have 35 minutes out of this. So we are able to reduce the dyes with different, as you see, TM5, 5% of MOS2, 10%, 20, and 30% of MOS2. So we started putting MOS2 into MOS2 layers. These are all two-dimensional MOS2 layers, which I showed in the beginning, onto the TiO2 systems. And then we can change the photocatalytic properties and also the adsorption rate. The dye will be adsorbed immediately, but it is saturated after 30%, as you can see that. And then we are also do the adsorption and photocatalytic property at the same time, which is very important for reducing the dyes faster to make it colorless. And we did extremely what is happening both in situ and ex situ. So we did the XPS and see the morphological changes, well, now not only on the system but also on the electronic properties. As you can clearly see that there is changes are happening in the molybdenum surface and also on the sulfur sites. And this is a real dye which we tested. It's a denim dyes coming from our denim shirts, and we are able to reduce the dyes with solar cells. We connected our electrodes to solar cells and then printed. These are all printed electrodes, our plasma deposited electrodes onto the dyes. This is the dyes, and then the electricity is coming from the solar cells. So we are able to, as you can see, that at 0 minutes you have the dye adsorption, and then even after, say for example, half an hour or 40 minutes, for half an hour we were able to take the dyes out completely. I mean, so this we left the flocation because we wanted to show the difference between the reduced dye and the non-reduced dye. And the declarations are, we tried with different samples with 10, looks like the 10% has shown the highest declaration. And particularly we also used solar light, and we also used LEDs. Okay, so solar can only do in the morning, whereas in the daylight. Whereas if you wanted to introduce into the system, then we are using it white light. So we also reduce this white light and the UV lamp. And then you can clearly see there's not much difference in the decolorization between white light and the UV lamp. This is the one which we are currently in process in a factory in Tirupur, no, not Tirupur, Perundurai. So, and then after that we went to this project again funded by Royal Academy of Engineering, where we used nanofibers, the nanofibers that is coming from plants, particularly vetiver. And then we thought that it's better the photocatalytic system doing more work for this. So the stability is getting reduced. So we started thinking that why can't we go for nano biosystems. So we have done this implementation nano biosystems as well for wastewater treatment. I have only 10 minutes remaining. So there is another one which we also coated the plasma systems. It's very simple systems. We coated onto the copper, inside the copper, and you can see the plasma is generated here. And then the dye is, you can see that the dye between here and here, we are able to discolorize the dye with the 2D materials. So this is a fantastic system which currently being in progress. And we were able to even mix with the seawater, and we get hydrogen energy from the waste. As you can see that the bubbles are coming out here. These are all nothing but the evolution of hydrogen from the seawater, from the dye itself. Pretty much we are on, I think I'm on time. Then we started putting different materials, different 2D material systems, and we are able to get oxygen, hydrogen evolution as well as a function of as the hydroxyl radicals started to dissolve, and the pollutant is breaking into hydroxide and oxygen radicals. It's about 20 minutes remaining. And then thank you very much for your attention. I think I leave it 5 minutes for questioning. Thank you.
Dr. Arya, sir, you can ask the questions from the audience. The private chat you have, right?
Yeah, fine. Is the audio is okay? Am I audible?
Yes, yes sir. Yes, sir.
Thank you, Professor Krishnamurthy, for the illustrative lecture, Science, Technology and Society. You have shown large number of materials to be used for application. And there are a few questions by the audience. And of course, I have two, and maybe two other from other faculty too. Just the first question is about external boron nitride. Can you exfoliate external boron nitride similar to graphene, the liquid exfoliation method?
Yeah, it has been tried, liquid exfoliation for hexagonal boron nitride. And it is, as I said, it's very difficult to exfoliate hexagonal boron nitride because of the van der Waals interaction between those two. So we have to have a, say for example, in terms of graphene, we were able to extract through even a simple solvent called NMP. Okay, and this NMP goes and sits in between them. And also when we heat the NMP, because NMP helps to take the layers out when you sonicate. And when you heat the systems, this NMP will also take through some of the bonds with it and leaving a very highly uniform graphene. Whereas in the case of hexagonal boron nitride, it is getting much more challenging because the dislocations are happening when you use the proper identification of still proper solvents for large scale HBN is a challenge.
Okay, thank you. The delegate may ask to correspond with him for further discussion. The next question is about can you exfoliate, for example, 2D oxide material? What method that you suggest for oxide materials, 2D to exfoliate oxide materials, say MOO3 or something like that?
Yeah, you can use hydrothermal systems. You can use simple hydrothermal systems to heat the systems, and then use high-end ultrasonication. I think MOO3 exfoliation is easier.
Okay. Similarly, the next question is about a 2D hybrid organic, inorganic single crystal for solar cells. Would you like to comment on that?
This is a challenge. 2D single crystals. Okay, yeah. Single crystals, organic and inorganic systems. Okay, it is a challenge, particularly the heterostructures of single crystals, right? So you may get defects. You cannot get absolute single crystals. It's very difficult, particularly. So, and if you are talking about organic solar cells, there is quite a lot of work on crystalline 2D materials, but I don't see anything on single crystals of both sides. It's difficult to do, and if it all can be done as well, are we gaining more on that? I'm not sure.
Okay, thank you. Next one is about the solar cells. Is it the material is important or the architecture is important? It's a generic question, but yeah, both.
Both definitely. Materials is also important. But if you're talking about now, after the introduction of organic perovskite solar cells, we all know that MAPB structure is toxic, and also MAPB is also unstable. And so what people have now gone is a combination of both silicon and MAPB structure. I mean perovskites. Okay, there is still heavy research is going on heterostructures of silicon and perovskites, and in my opinion, I think that's where the future might go, by the combination of silicon and organic solar cells. So I think that kind of answers the question.
Yeah, fine. There are three more. Quickly go through the questions.
So we're talking about you were talking about inverted architecture in terms of organic, and the different architecture in terms of silicon solar cells. So the architecture and the material plays an important role.
Okay, this
both needs to be important.
Yeah, fine. Next one is about this this recycling of the solar PV. What is the latest happening?
Right. Oh gosh. Right. So recycling is a huge business.
Okay.
You leave about solar as well. Okay, recycling solar is a small business. Whereas if you go into recycling of batteries, so there's no, say for example, there's no life without batteries these days. Probably there'll be more batteries than human beings. So recycling of batteries is a huge challenge, and people, particularly lithium-ion batteries. So probably that's a project which we are currently working on, and extracting not lithium batteries. Lithium is not a major component here. But the cobalt is a major component. How to recover the cobalt and recycle the cobalt. In terms of recycling solar cells, you can recycle particularly the silicon, but there are challenges there. That is why I was talking about silicene. Okay, if we can method to extract silicene by either plasma technologies or any other non-invasive technologies to extract silicene from the silicon, then you have a market for that, and when you extract that, then you can put those into flexible substrates. So there is a huge research can also be undertaken in particular of recycling of solar cells.
Okay, thank you. There's a question on COVID. For example, can we employ the 2D nanomaterials to detect COVID? For example, to make a device or something to be
See, it's COVID illam valkai illam podrukku. So yeah, the thing is like why we need to have 2D materials in the thing. So sensitivity will increase, and also the surface area increases. Okay, but what happens to the virus? Because we currently, to be honest, in many areas, particularly in many countries, there is a less interaction is happening between the biologists and the others. Well, there are less virologists, to be honest. So it's very difficult for us to interact with virologists to understand how the virus will impact with the 2D systems. There could be something can be done, but it is still further exploration, and I don't see anyone has been doing. But all theoretical explanation, you can see millions of papers are there, but nothing concrete, I don't think, has been done physically. But also it is difficult to do that as well, as the virus mutates into different forms. That is my assumption.
Thank you. There are three more questions. Rajan Babu, can we have three more questions, or time is there?
As a chair, you can decide, sir. No problem, sir.
Okay, fine. I'll go through, because that's session I was worried. That's okay.
Yeah,
fine.
Next oral presentation only. We have enough time.
Okay, fine. So next question is about
if Professor feel comfortable, we can continue.
Yeah. In the morning times, okay. Yes. What is the efficiency of organic solar cell if one uses a graphene oxide as transport layer? Are you working on both conventional and inverted solar cells? What is the efficiency of inverted solar cell with the graphene oxide as interfacial layer?
Yeah, it is a very good question. This is what we are doing here, actually. We are using modified graphene oxide surface, not as an interfacial layer, actually. We are using this as a whole transport layer itself, because the whole transport mobility is increased. Okay, so we are using where there's a whole transport layer, and we can see that the conductivity of this increased when compared to the spirometad, which is another whole transport layer. So we are now currently in the process of, particularly if you're talking about perovskites, so we have got close to about 18%, but we are pushing it no further. We wanted to understand the stability. So we are working on the stability test. It's still not published yet.
Okay, thank you. We'll have 5 more minutes. Okay, just 3 more questions. Can we grow MBE, this 2D materials? By MBE, can we grow this 2D layered materials?
Good question. Yeah, of course, you can grow. You can grow anything in MBA.
Anything.
You can speak more than that about than me.
No.
Yeah, you can grow MBA actually. Yeah, you can grow particularly if you have the good precursors or the targets you have. With the targets, particularly with the one which I am talking, the graphene, the silicene, germanate, and stantate. These can be grown by MBE easily. Or even if you can also use a laser MBE, also use a particular laser and shine the target and then try to take few layers out and then deposit on the surface. There's always a possibility. And MBE is another extremely good tool, particularly when it comes to spin electronics devices.
Okay. Next question is on the 2D materials for scratch and shock resistance coating, which could be put on mobile phone or computer systems. 2D layered materials as coating, shock resistance, scratch and shock.
So shock resistance, okay. Yeah. If you go, I think we are currently working with a company called Lohmann Technologies, and we are working with them particularly on this subject, on the scratch resistance, not only on scratch resistance, but also on increasing the conductivity of this 2D material, and that can be incorporated directly onto the, I can't say mobile, wearable electronics. So what we are doing is we are changing the properties and then printing or depositing them onto their flexible tapes. So they have a flexible tapes like what we have, cellophane tapes, and then we incorporate this material directly onto the porous tapes, and then we will do all the electronics and other characterization and incorporate them. And when they elongate along one particular direction, the stretch, we further able to increase the conductivity because of the stretching elongation. Particular bonds will get to oriented along the direction. So it is a fantastic research which we currently working, and it has gone into commercialization stage.
Okay, thank you. Let me have the last question. This MOS2 single layer, is it scalable? Because graphene, single layer graphene, I think can be scaled up. I am not following literature. Whether the MOS2 is also possibly to mass produce, or at least gram quantities I'm asking.
See, the trade is the same for both MOS2 and graphene as well. Okay. See, people are, again, I'm being a purist actually. So to me, graphene is a single layer.
Single layer, okay.
Anything goes beyond 2 or 3 or 4 layers. People still say that up to 4 or 5 layers, you can still say as graphene, but the properties are different. And similarly, MOS2 is a similar stacking structures. But MOS2, advantage of MOS2 is it has a sulfur in it. So you can still play with the sulfur as I showed you the fluorescence. The fluorescence is a critical part because from the indirect band gap to the direct it has gone into, then it has become fluorescence. Until that time, we get that property, we can able to scale up. And particularly if you are asking, hydrothermal methods is a very simple method. When you are able to make it through hydrothermal method and all it needs optimization, I'm pretty sure that MOS2 is easily scalable. And there are MOS2 2Ds are available in the market itself.
Okay. Thank you, Professor. Professor Rajan Babu wants to ask a question.
Sir, Professor Krishnamurthy, thank you very much. One personal question.
Hello, Rajan Babu. Vanakkam.
Yes. Yeah,
I met you actually about 20 or 15 years back.
No, 2012. 2012 conference.
2012, is it? Okay.
Yeah. Related with that only, I'm going to ask one question. You visited VIT 2012 for our conference, and you gave wonderful talk. Today also you are giving very good talk, and it is excellent as 2012. From where you are harvesting energy to maintain this kind of talk?
Rajan Babuji.
Thank you.
Keep us smiling, right? The smile and positive energy is contagious.
Yes, thank you, sir. Thank you very much.
And we got some wonderful students. So the students are, this is like not our job. For when 2012, it is some of my work. Now our things has gone. Now we have got good students, and it is like you won't believe. Like there's no hierarchy between student and us. Like
yes.
lunch together, we have fun together. So it's a family. I think I wish I would. I wish you could also join us at some
next
stage.
time next time you visit India, please visit VIT also.
Sure, Rajan Babu. Always pleasure to come. Thank you.
Thank you very much. Sorry,
thank you. On my personal side, I must thank Professor Krishnamurthy for recalling MSRC. I think we used to be independent, and I don't know, we used to work late hours and all that. I was doing this project, I think MSc project was doing. And okay, on behalf of the organizing committee, it's my pleasure to thank Professor Krishnamurthy for sparing his time and for the excellent lecture. Thank you, sir. Thank you.
Thank you so much, and please all stay safe and let us keep smiling even though we are in the tough times. Thank you so much for the opportunity, and I take a leave. Thank you.
So on behalf of the organizing
we will correspond with you. I will correspond with you, Professor Krishnamurthy. Okay, Professor James,
Yeah, on behalf of the organizing committee, we thank Professor Satish Krishnamurthy for the excellent talk, and he has given a motivation to the youngsters. Thank you very much. And also, we would like to thank Dr. Vijay Raghavan for chairing this session. Thank you, Professor Krishnamurthy and Professor Vijay Raghavan. Thank you.
Thank you.
Thank you, the organizing committee. Thank you. Fine.
Yeah. Participants, now we are going to oral presentation session, and the session 3 candidates, you will continue in the same link. And for the session 4 candidates, you can see the chat box, and also we have sent you the link in the mail so that you can switch over to the mail session 4 candidates. So we are going to commence the poster session now, oral presentation now. So please be ready. Now we are going to start the session in a couple of minutes. So please be ready with all your presentations. And tomorrow morning at 9 o'clock, the third session will start. So thank you, one and all.
I'm signing off. Thank you.
Hello. Hello. Good afternoon.
Hello.
Hello.
Yeah. And Tarun here. We can hear you.
Yeah. Okay. So
I'll be with you in this session. I'm the session in charge, and thank you for accepting our invitation for being a panel member. Hello,
it's okay. It's my pleasure.
Hello, Dr. Ashutosh.
Oh, hi.
Yeah. Thank you for being a panel member.
Yeah, it's our pleasure.
So we will start in a couple of minutes. I hope you have received the evaluation sheets.
Yes.
So, Dr. Lakshmi Narayan and Dr. Ashutosh, let me tell you, we have 8 minutes for presentation and 2 minutes for question and answer for each oral presentation. So we will request our presenters to stick to the time so that we could finish our session in time. And I will call the presenter and you can judge the presentations. Right? I have the session plan with me. I will call the presenters according to their number.
Okay, right.
Okay, so I guess we can start. In the meanwhile, the first presenter shares the screen. Others can be ready as well. So, hello. Somebody has muted me. So first presenter in session 3 is Mr. Ayan Banik, and the title of his presentation is Arduino Operated Smart Green Hybrid Energy Harvesting for Sustainable Rural Development. Mr. Ayan Banik is there?
Yes, we are ready. Can you join?
I guess he is not there. If Mr. Ayan Banik is not there, the first presenter, can we call second one? Dr. Ashutosh?
Yes.
Can we call second presenter? Mr. Ayan Banik, the first presenter, is not here.
Yeah. Please.
Sure. So, Mr. Amrit Kumar Thakur, second presenter in this session. The title of his presentation is Improving Energy Harvesting Significantly Using Reduced Graphene Oxide Nanosheet for Solar Desalination Application. Mr. Amrit Kumar Thakur. Oh, Amrit is here. Hello, Amrit. Mr. Amrit Kumar Thakur.
Hello, Professor. How are you?
I can see him in the participant list.
You can share. Maybe I can share this one.
Yep. Mr. Amrit Kumar Thakur, are you there? Yes. Yeah. We can see you, but we cannot hear you. Okay. Mr. Amrit, you are not audible. We cannot hear you. Hello. We still cannot hear you.
I think his connection with the microphone looks like is.
If you are using a laptop, can you use your laptop's mic rather than using microphone?
Okay, otherwise, Tarun, let's call the next one, no? If, by the time he can settle his mic.
Yeah, sure. As I can see, the third speaker is also not here.
He's connected. I think we need to unmute him. I think he connected. Amrit Kumar again.
Hello.
Yeah, we can hear you now.
Oh, okay. That's great.
Can you share your screen, please?
Yeah. Sure. Yeah, kindly allow my screen to be shared actually.
Just one. Ankur. Just 1 second.
Yeah, sure.
Yes, I guess now you can share.
Okay.
Yeah, you can see your screen.
Shall I start?
Yep. So you have 8 minutes to present and 2 minutes for question and answer. So please stick to the time. Thank you.
Hello everyone, this is Amrit Thakur from Anna University, PhD scholar in Department of Mechanical Engineering. My topic of today's talk is improving the energy harvesting with the utilization of, excuse me sir, I think someone is on the mic, I'm getting some disturbance. Hello. Okay, okay. Yeah, so my talk of today's is reduced graphene oxide for improving the clean water production. So basically, the like 97% of total available water is saline, and only 1% can be used for the drinking applications. And there is a tremendous need due to the growth in industrialization and urbanization, and we are facing a lot of challenges in producing clean water. In this particular sheet, in zone wise, India is having the high stress on water productivity. So there must be some alternative options to improve the quality of water and to produce clean water. In India, we have abundant availability of solar energy, and with the help of solar energy, we can distill our brackish water into pure water with the help of solar desalination system. Solar still is a device which is used to convert the brackish water into the clean water or pure water with the help of solar energy, or harvesting solar energy to produce clean water. But the major problem is low productivity of this device due to the lower absorption characteristics of water. And the major research work which has been carried out by our group is to improve the productivity of this device, or to improve the energy harvesting with the utilization of reduced graphene oxide coating on the solar steel, to improve the water purity and to improve the energy harvesting characteristics. So in order to achieve the target, firstly, we have synthesized reduced graphene oxide with the help of graphite. Graphite has been converted into graphene oxide using Hammer method, and the graphene oxide has been further converted into reduced graphene oxide with the help of thermal reduction. Due to the thermal reduction, we got the wrinkle structure, which is clearly visible in the seam, and the size was found to be in the range of 20 to 80 nanometer. The XRD shows the carbon percentage in the prepared graphene oxide was around 89%. Then the characterization was done. Sim images shows the hierarchical porous structure. The BET shows the specific surface area of 167.72, and the largest pore size was found to be 70 nanometer, which was achieved using BGT testing. Once the synthesis of RGO was completed, then we moved to prepare the nanopent, which can increase the solar energy harvesting, and which can automatically improve the output of our device. So RGO was selected as a nanoparticle in the mixture of black paint and turpentine, which was taken as 4:1. Then we have mixed the RGO. After that, we have performed magnetic stirring. Then we have achieved the homogeneous solution, and further we have gone for probe sonication to achieve a complete thorough mixture of nano paint, which is basically a mixture of black paint with reduced graphene oxide, and two different composition was prepared, that is 2% and 4%. This particular shows the algomerates of RGO formation in the nano paint, and after performing this, we have coated into three different absorber. One absorber coating was done using the spray gun with the gun nozzle of 1.4 mm diameter. So these are the devices. This particular absorber was coated with only black paint. This absorber was coated with black paint plus 2 weight percentage reduced graphene oxide, and this was coated with 4 weight percentage reduced graphene oxide mixed with black paint. Different temperature sensor was used to measure the temperature across the junction, and solarimeter was used to measure the solar radiation. The most important characteristics regarding harvesting the abundantly available solar energy is the absorption of solar energy. So solar absorption must be performed to evaluate our results, and we have seen that RGO has given the significant solar radiation absorption, which was found in the range of 99.18 and 99.99, whereas water has given this significantly low in the range of 20 to 40. This was performed in the range of solar radiation, where we used to get the solar radiation in the range of 400 to 1100 nanometers. After performing the UV characterization, then we have moved to the effect of nano coating on improvement in energy harvesting. So this was the solar radiation, and the peak solar radiation was observed to be 1096 watt per meter square at 1 p.m. In this respective solar radiation, we got the peak absorber water and glass temperature respectively as 48.5 degrees C, 54.4 degrees C, and 57.6 degrees C. This was the case where only black paint has been coated to harvest the solar energy and to convert it into the clean water. Then we have moved with 2 weight percentage reduced graphene oxide, where we can see that there was a significant jump in the temperature, and we observed the temperature across absorber, water, and glass to be 49, 56, and 58 degrees C. With the further increase in reduced graphene oxide coating percentage, this temperature was further raised to 51, 57, and 60 degrees C across the 3 junction. So basically, the mechanism behind this is larger pore size leads to exceptional increase in solar radiation, and this solar radiation will leads to increase in the rate of evaporation and condensation, which will ultimately produce the clean water for our device. So we can see that temperature across the junction with the help of reduced graphene oxide coating was varying, and with improvement in the with the increase in reduced graphene oxide percentage, there was a significant jump in the temperature across all the 3 junctions. With this, what we have achieved that with the black paint, we got the clean water production of 3.96 liter per meter square, whereas with increase in mass concentration of reduced graphene oxide, it can give us the increment in fresh water production of 14.4% and 25.5%. Further, we have increased the, we have evaluated the efficiency and the water
Amrit,
efficiency.
Amrit, you have only 1 minute left, so please conclude.
Yeah, sure. So efficiency was calculated, and we got the maximum efficiency of 38.5 with the 4 weight percentage. All the parameters was evaluated for clean water, and we got all the character of clean water under the limit of BIS standard. So we are concluding that RGO was the excellent energy storing material for improving and harvesting abundantly available solar energy. It has given highest UV absorption. Utilization of 4 weight percentage RGO improved the water and absorber temperature by 6 and 7% average. Utilization of 4 weight percentage RGO has improved the water yield by 25 as compared to the solar steel without any coating. And this low cost developed RGO will be helpful in achieving fresh water production, which can be highly utilized for rural population across the globe where we have abundant availability of solar energy.
Okay.
Thank you so much for listening, and thank you so much for giving me the opportunity.
Okay, so I have a question that how did you calculate this absorptivity percentage? In one of the slides, you have this absorptivity plotted. So normally we plot absorbance, and then you have plotted in percentage, right?
Yeah, actually.
So it is.
Yeah. So for water, actually, it was performed in the band range of 400 to 1100 nanometer. We took normal water in a crucible where we have got the value of, with the varying range of UV spectrum, we got the varying range of particular spectrum absorbivity, and then we have converted that absorbivity into the percentage. So we got this value it around 22 to 40% in the case of water, whereas it was maximum for RGO, which was around 99%.
Okay, but water also have a strong absorption in infrared regions, right? So did you take care of it? Like, did you subtract those?
Yeah, actually, I basically it was observed after penetrating through a particular surface, so that intensity and these things may vary accordingly, and water usually used to perform lower radiation as compared to black material. So we got the value around this percentage only.
Okay, so I think the audience, even they also have the questions, I guess.
Yeah, I have one question regarding the same plot. So you say that with this reduced graphene oxide, your absorption is better, right? Compared. So, but this curve shows it around 99%. So is that the same plot? Can you can you go to the page? Yeah. So is that the artifact of your black paint, or I mean, how do you make sure that this is? Did you test it with only with the black paint and compare with the RGO with black paint?
Yeah. I will come to that point. We actually, that paper is under review. That's why I have not presented the result. With only black paint, we have got the absorption around 94%, while addition of RGO has improved that percentage to 99. So there was not much jump with black paint and RGO, but the major role was played by the RGO higher thermal conductivity. If the thermal conductivity of RGO is higher, absorbed radiation can be quickly transferred to the water, and the transfer of that particular into water will give rise to the immediate evaporation effect. This immediate evaporation effect will lead to the immediate condensation, and through this we will going to achieve the maximum productivity of water. So not only UV characteristics of RGO is playing here, because we have got the RGO thermal conductivity much greater than graphene oxide thermal conductivity. So it's a synergetic effect of absorption as well as thermal conductivity, which is going to ultimately give us the water productivity much better than the simple one or the conventional one where we have coated only black paint.
So with the black paint also you got a flat curve for all wavelengths?
No. Actually, it was not from 400 to 600. It was different. After 600 to 900, it has given a peak value. Then suddenly it has gone down. So there will be a deviation in that range according to the UV values.
Okay. So I think there is one question. I think that we can take it as a last question. That one, Mr. Shiv Kumar. Shiv Kumar is asking that oxygen is a gas. Then how are you identifying from ETS?
ETS, it's actually XRD. I will come to that point also. It's a XRD. Okay, so here our major contributors are carbon and rest, because it's basically the constitute or the form of carbon. So our main focus is to obtain the percentage of carbon. Rest all are not major constituent for us. So what we have achieved from XRD, that we have got around 90% of the carbon, and rest all are the insignificant, which is not going to contribute for our result. So we have not considered that part. XRD was carried out just to check the percentage of carbon.
Okay. Thank you very much.
Yeah, thank you.
Okay, so Tarun,
yeah.
Next is.
Yeah, so next speaker is Dr. Rambabu V.
Okay.
Dr. Rambabu, can you switch on your video, please? Dr. Rambabu V, and his title of presentation is Machine Learning in Efficiency Improvement of Wind Energy Converters. Dr. Rambabu. Okay. Dr. Rambabu. Hello. Yeah, he's starting.
Hello. Hello.
Yes, we can hear you. Yes.
Is my screen shared?
Yeah, your skin is shared, but it's like not full one. It's, I think it's only, we can see only the partial. Yeah, now we can see it.
Yeah. This is the machine learning in improvement of wind energy converters.
Okay.
Wind energy converters, wind is the one of the promising renewable energy source available free of cost. The fast depletion of fossil-based natural resources and exponentially increasing energy demand across the globe are the motivation for exploring these alternative energy sources. The wind is a seasonal energy. It is not continuous. So we need to harvest when the wind is available plenty in the particular season. And this is also highly location dependent. In all the places, wind is not available all the times. Wind is there. Various places are surveyed for the availability of wind, and accordingly, wind energy plants are selected, locations are selected for that. Now, wind energy conversion depends on the direction of the wind and which varies with time. The wind conversion efficiency is good between the wind speed when it is 6 meters per second to 12 meters per second. The rest of the times, below the 3 meters per second and 12 meters per second, about 12 meters per second, the conversion efficiency is very poor. Now the problem is here, we need to harvest and shift or promote the wind energy to sustain the requirement of the future energy demands. But however, the wind energy conversion, the people are not going because of the two major reasons of its low conversion rate efficiency. The energy converters are fixed. The reason is energy converters are fixed in one direction. And this is also based on the wind cruise analysis. And as a result, the considerable amount of wind that escapes away from the wind energy converters blades. Here we have 2-blade, 3-blade wind energy converters. And running the wind energy converters during the low wind, that is less than 6 meters per second, that means the energy is pumped into the wind energy converters rather than the energy is generated. So this is what we can say, the negative energy generation. So unless it is monitored, the conversion efficiency of wind energy converters cannot be improved. Though the first reason for not going for this wind energy conversions is higher cost, higher initial investment. And second is, even though you have the higher initial investment, the conversion efficiency and conversion rate is low because of these two major reasons. If you can solve these issues, then it is possible that the wind energy is one of the prime energy source for the future energy demand. Yet, what others here we address these issues by a wireless networking technology and a machine learning concept. Here, the major investment, after the major initial investment, the second is the maintenance of energy turbines is a very costly affair because the turbines are so high and personnel going, climbing the energy turbines and doing the maintenance work is a costly affair and a very periodic activity to be done is a difficult task. And once the wind energy turbine, if the periodic maintenance is not there, if the turbine breaks down, that will result into major losses. So here what we are doing is, we are acquiring, just I'll go back and go ahead. This is a wind energy converter. I have taken the hybrid system here, wind energy and solar energy converter, solar energy conversion system, hybrid conversion system over here. But my focus is on this wind energy converter. Here the various parameters of this wind energy converter are monitored.
Yeah, you have a. I think you have a last 1 minute, so please hurry up.
Yeah.
Dr. Ram Babu.
Okay.
So,
I think
I think you can summarize your results and your own contribution.
This is the contribution. We have acquired the parameters using wireless sensor network instead of going the personal to the climb the wind turbines. And these parameters like high level temperature and speed of wind machine are acquired, and that information is transferred through web interface here. Then the results, this is the part of the result. You can see this is a plot taken from Windows in one day. That is data available in the Windows data in one day. Here it is that the wind speed, the y-axis is the wind speed, and x-axis is the time. Then wind is changing in speed. It is not a constant one. So here, if you see that this is a conversion rate, conversion generated in terms of watts. Sometimes it is having a zero energy also. And at this point, the feed energy we are feeding to converters and energy generated out of the converters is quite different. That means we are going into negative energy generation. So this point can be solved by analyzing and training the wind energy converter to orient itself in the direction of maximum wind flow. And whenever the wind speed is less than 3 meters per second, we can stop the wind blades by stalling the wind blades. And whenever the wind speed is more than 12 meters per second, again, we can apply the brakes and the generator should be stopped. So this type of training based on the wind energy data, we have given the training to this system, and we have used the reinforced learning machine system based on the over a period of 1 year data at the particular place. The machines will automatically adjust to the training, and the conversion efficiency can be improved. This is what we have experimented, and the results are seen.
Okay, so it's very nice. So if audience have any question, then they can post.
Yeah.
Okay, so Dr. Ram Babu, I have a question that how many data you, for machine learning program, right? You need to have many data points, many data, exactly, so that you can learn something from that and then use it in your program,
exactly,
right?
Exactly.
So how many data points you are using it? I mean, it's like how many data sets?
I think we have taken around 12,000 points we have used.
Okay.
But not to go for, actually it should have been better if you go for higher data.
Yeah, that's what I was thinking.
Wind energies having 20 years of data is available actually, but we could not use that much. We have used only just 12,000 points and just tested in the trial basis. This is a simple experiment.
Okay, so very nice. Yeah, very nice.
Thank you, sir. Thank you.
Okay, so I think no one is having any questions. So Tarun, we can go for next presenter.
Okay, thank you very much, sir.
Thank you very much.
Right. Welcome.
Ningroj. Mr. Ningroj. Mr. Ningraj is there.
you are in the right.
Could you please, yeah.
Conference.
Unmute your mic. Yeah. Please share your presentation. Right. Ningraj, please unmute your mic. Ningraj,
You can use Control A. Control A. Press. You can use Control A to unmute. Yeah. Control A is not working. Press. Take or Alt A. Just a minute.
Okay. Just a minute, sir. Just a minute. I didn't make him co-host. Now he can do.
Okay.
Can you do now? Do it now.
Yes, sir. Yes, sir. Now it's.
Yeah, fine.
Okay.
It's my screen visible, sir.
Yeah, it's coming up. It's coming up.
One second, sir. Shall I start, sir?
Yeah, please go ahead.
Good evening, everyone. I am Ningraju, Junior Research Fellow working in Center for Nanomaterial Sciences, Jain University. Today, I will be giving my talk on the development of novel green and non-convection heterogeneous catalyst towards sustainable production of biodiesel from waste cooking oil. And this work has been done under the guidance of Dr. Sakar Mohan and Professor Geeta Krishna in Center for Nanomaterial Sciences. And I am from Biofuel Research Laboratory, Jain University. And this is the outlook of my presentation, which will be covering in further coming slides.
Ningraj, somehow I'm not able to see your slides.
It's coming, sir.
So no, I think it's only says that you have started screen sharing, but nothing is on my desk.
But it's coming, sir, here. No, sir. Now it is coming, sir.
Okay, let me see. No, it's not. But is it visible to Tarun? Tarun, are you able to see?
Yes, sir. Sir, you are right, actually. It is not visible to everyone.
Is it not visible to everyone, right?
Yeah.
But
now
it is.
Now it's fine. Now it's fine. Yes. Yeah, now it's fine. Yes, please go ahead.
This is outline of my presentation: introduction, biodiesel overview, objectives, materials and methods, followed by results and discussions, summary and outlook, and acknowledgements. When coming to introduction, India is facing major problems such as overpopulation, industrialization, aging infrastructure, overconsumption, energy wastage, and use of non-renewable energy. So in this way, we are majorly working on the production of rapid production of some of the sources, such as by using waste, such as green sources, and we are mainly focusing on production of biodiesel. So rapid growth in transportation, industrialization, and civilization from time to time causes increase in requirement of fossil fuel as well as energy. So India ranked at 5th at global level on overall consumption of fossil fuels. So all these led us to search an eco-friendly and sustainable alternatives. So in this way, biofuels are the initiative which raise hopes for finding such alternatives. Generally, biodiesel is produced from vegetable oil or animal fats. And nowadays, heterogeneous catalysts are prepared for biodiesel production as a compact of various advantages such as reusability, easy separation, and eco-friendly. And in this figure, you can see that many of the reports says that in coming 50 to 100 years, all the diesel will be empty. So this is the condition after 50 to 100 years, as shown in the figure. So when coming to biofuels, biofuel is a fuel which is produced from vegetable oil, organic products, and wastes. So based on feedstock source, we have first generation, second and third generation, and based on chemical nature, we have bioethanol, biodiesel, and others. In our work, we are mainly focusing on production of biodiesel. And what is biodiesel? Biodiesel refers to vegetable oil or animal fat-based fuel consisting of long-chain alkyl esters, which may be ethyl, methyl, or propyl. It is made by chemical reaction of lipids with alcohol containing fatty acid esters. So this is produced by a process called transdisciplinary, whereby glycerin is separated from fat or vegetable oil. In our work, mainly we are using vegetable oils, and this is the typical reaction where when triglyceride reacted with methanol and traditional catalyst NaOH, we'll be getting mixture of fatty acid esters. Fatty acid methyl ester is the name of biodiesel, and with side product as glycerin. And these are some of the different sources that we are using in our work. Plant seed oils, used cooking oil, and algae is our feature work. And these are some of the non-edible sources we are using in our work. And when coming to biodiesel production methods, we have homogeneous, heterogeneous, and other methods. But in these three, we are mainly focusing on heterogeneous catalyst methods because of many advantages, such as non-sensitive to free fatty acid, and recyclable, eco-friendly. We are using some of the nano catalyst also with along with heterogeneous catalyst. And this is a flowchart for biodiesel production. If we are depending on feedstock, we have to collect the feedstock and we have to extract the oil by using mechanical expeller. After that, the oil will be filtered. The filtered oil will kept for 24 hours to complete settling. And then next we'll be taking testing if free fatty acid content. If free fatty acid is less than 2, then we'll directly go for transesterification reaction. If the free fatty acid is more than 2, first we have to do acid esterification with methanol and acid catalyst SSO4. In transesterification, we can see phase separation where biodiesel is upper layer, middle will be catalyst, and after will be the glycerin. And after that, we obtaining crude biodiesel. It should be dried, and purified biodiesel can be used in diesel engines. And these are some of the green sources that we are exploring in our work, like banana peels, banana pedicles, orange leaves, orange rice husk, eggs, etc. And these are the objectives of my study, which will be explaining in coming slides. And this is the materials and methods. Is the first paper that we have done in our PhD. Synthesis of copper oxide nanoparticles using Terminala cebula, green leaves. Like this is the protocol that I followed for preparation of plant extract. Leaves were collected and dried leaves were powdered and subjected for saltless extraction. And aqueous solution was dried in water oven for 60 degrees. And this is a plant extract that we prepared. It acts as reducing agent, and this is a protocol for synthesis of copper oxide nanoparticles. And this is the overall flowchart that we used Terminala cebula leaves as well as Terminala cebula seeds for oil, and we use this biodiesel production. And this is a this is the results and discussions where in XRD shows monoclinic crystal system, and crystallized size was found to be 21 nanometers using Serres equation. And in UV visible spectra, we observed broadband around 300 to 500 nanometers. Either in the range of visible light driven property it is showing, and band gap was calculated by Toxplot, that is 2.35 electron volts. And when coming to FTA spectra, we observed major peaks such as OH groups in 3407 and 1605 stretching vibrations, and CH weak vibration at 2851 and 2919, and CuO metal oxygen bond was found in 532 centimeters inverse, which confirms the presence of copper oxide. And when coming to BT analysis, it shows the type 4 isotherm, and surface area was found
Okay,
to be.
so Mr. Ningaraju, you have last 1 minute, so
Okay,
please.
sir. And FSM analysis, DLS also carried out, and this esterification process, transesterification, and FTI spectra shows good information about the biodiesel, and NMR spectra also shows the proper results. And this is the one MSNM reporter that we used in biodiesel production, and you can see clear separation of biodiesel, glycerin as well as catalyst. AR spectra shows some important peaks also, XRD well matching with SiO2 data. And surface analysis, surface morphology shows uneven morphology as we select natural reliable sources. And this is some new work, gasoline fuel we used for visibility, to increase the visibility. And these are all results and discussions related to that, the influence of catalyst, temperature, and other parameters. And this is also some new strontium oxynitrate in biodiesel production as a homogeneous and heterogeneous catalyst. And this is one of the new concept that we developed. We use of ginger extract to reduce the viscosity of the biodiesel produced. And this is a produced ginger extract. And this is that we followed. Biodiesel, glycerin, and catalyst is well separated, and we are mainly working on challenges in biodiesel to increase the calorific value and freezing point. So if synthesized biodiesel will not change its properties after 3 to 4 months, so we are mainly working on that. And when coming to summary and outlook, we synthesize three heterogeneous catalysts: copper oxide, sodium oxynitrate, and sodium titanate, and utilize these three catalysts in biodiesel production. The yield of using copper oxide was found to be 93.5, which sodium oxynitrate was 96, and sodium titanate was 97. This on special work, we synthesize ginger extract and use successful for reduction of viscosity of the biodiesel. And ongoing works and some work further optimization need to be done, and engine performance and combustion studies need to be done. And coming to acknowledgement, I acknowledge my guide, Dr. Sagar Mohan, for continuous support and guidance, Professor Geeta Balakrishna, Director of CNMS, for our continuous support and guidance, DST Nano Mission for funding, and JN University for infrastructure facilities, all organizing committee members of VITC 2020 for giving me an opportunity to present my work here, faculties, research scholars, and non-teaching staff for CNMS. And this is our group, Biofuel Research Laboratory at CNMS. Thank you for giving me the opportunity.
Okay, thank you so much. So okay, thanks for very nice presentation. I think so. What are the ways you have a yield, right? You have like 97%, 98% yield.
Yes, sir. Yes, sir.
But what are the ways to increase the yield? Increase the yield of this production, right?
Yes, sir. Yes, sir. It depends on the selection of feedstock. If you're taking if you're taking waste cooking oil, we're getting around 96, 97, 98% yield. If you're taking any seed oils, maybe the yield will be increased like 98, 9, like that. So we are in our work, we are mainly focusing on the production of biodiesel using waste cooking oil, as it is abundantly available in our canteen, so college canteen campus. So we're taking that and we're using. Some of the works also we are done using seed oils. That time we are getting around 98% yield, like that, sir.
Okay, so if there is any question from viewers, then they can ask. Okay, so if no, then I think I would ask, I would invite the other presenter.
Thank you, sir. Thank you very much.
Okay, thank you so much.
Hello, the next presenter is Dr. N. Rajeshwari Yogamala, and her title of presentation is Nano Confined in Doped Ag2S as Light Sensitizer in P photovoltaic cell.
A very good evening to one and all. Sir, is my voice is audible?
Yeah, I can hear you. Yes, please go ahead.
Okay, sir. Thank you. I am Dr. N. Rajeshwari Yogamala, Associate Professor in Physics from Vellore Institute of Technology. My presentation is on nano-confined indium doped silver sulfide as light sensitizers in PV cell. Today's scenario, as per today's scenario, the need for new, clean, and renewable energy sources to meet the energy crisis are rising. So the scientists and engineers works to upgrade the energy harvesting to a maximum based on the three triangular golden rule, mainly the efficiency, lifetime, and cost. The efficiency is determined from the fraction, how much amount of the input solar energy is converted to a profitable energy and functionality of the material. The lifetime is determined from the stability of the material and long range working process that the material has to, or the product has to work for more than 20 years without any loss in its efficiency. And finally, the cost, which depends upon the earth abundant raw resource material which are available and environmentally friendly without any toxicity to the product. Here in our study, silver sulfide is utilized as a light sensitizer. It is a 1,6 compound semiconductor crystallizing in a monoclinic phase. It has an narrow optical band gap of 1 to 2 electron volt and has a mixed ionic and electronic conductor, which is dependent on temperature. Why it is used as a light sensitizer? Yeah, a light sensitizer means a material should respond to the light energy or light of, especially focusing in the broadband spectrum ranging from the ultraviolet, visible and near infrared region. So it covers the optical wavelength from 300 nanometer to 1000 nanometer. Using as a light sensitizer, it has to match the energy levels of the conduction band edge of the semiconductor what we are using and the counter electrode what we are using. The third property of light sensitizer, it should be a quantum size, that is nano size, where the particles should be a spherical homogeneously so that they have a high surface area with good adhesions with long life excited state, which can inject more number of photo excited charge carriers that will help to harvest more light energy. Right, along with this, why indium metal has been chosen as a dopant in silver sulfide. We all know indium is a high ionic conductive material having an electronic conductivity of more than 10⁻⁷ Simon per meter inverse. So when such a indium 3+ is substituted in the place of Ag+ ion, more charge carriers of electrons will be promoted, and because of high conductivity, fissile charge transfer takes place. The second thing, it is acting as a hybrid and additive material in the material. So electron injections is very possible. So a multiple band transition is available, which can prevent the loss of electron and decrease the rate of recombination process. And the third point, the ionic conductivity or the atomic radius of indium is 156 picometer. Because of this high value, the more charge carriers can be promoted to the higher energy level. So there is an increase in the current passage and therefore increases the solar efficiency. So this is my methodology. So we prepared a zinc oxides and silver indium doped silver sulfide as a nano composite. So before preparing the nano composites, individual material compound are prepared as per the given procedure. So in zinc oxide, zinc nitrate and polyethylene glycol is used as a capping molecule. To have a white precipitate, sodium hydroxide pellets are used and hot heat treatment of 90 degrees Celsius for 6 hours is given. In silver sulfide, 0.4 molar of silver nitrate and 0.2 molar of sulfur is used. We all know silver sulfides are highly insoluble in a material. So to promote the solubility, ethylene glycol and C-tab is used for the solubilization. In indium doped silver sulfide, the same procedure is followed. Along with the silver precursor, the indium precursor of 0.4 millimolar indium acetate is added. So the zinc oxide, the prepared zinc oxide and indium doped silver sulfide is taken in the ratio of 4:1. Again, the heat treatment and the acidification measurements are given to promote the nano composite formations. So this picture shows the photographic view of the unsynthesized sample solutions. We can see the changes in the color. To specify the role of indium taken in this experiment, we have prepared the composites of two forms, zinc oxides and silver sulfide, zinc oxide and indium doped silver sulfide. So they are named as ZAS and ZAIS to mention the significance of indium in this role. So the basic synthesis tools and characterizations used in these methods are shown. So the basic characterizations to confirm the formations of the material compound and the crystal purity, we taken the X-ray diffraction. So the zinc oxide crystallizes in Woodside hexagonal phase with pure crystallinity and having a Scherer formula, average crystallite size to be 27 nanometer. In the case of silver sulfide, it again crystallizes in monoclinic alpha form with no second impurity phases. Again, using the Scherer equations, it's found to be 24 nanometer. And finally, in indium doped silver sulfide, we again have a monoclinic phase with no impurity present, as the indium ion having a high atomic radius of 156 picometer substituted in the place of Ag+1 ion with a 145 picometer. That is a shift, a red shift in the angle, and it is due to the tensile strain present in the lattice element. This shows the XRD pictures of the nano composite, zinc oxides and the silver sulfide. Here you can see it has a pure crystalline phase of zinc oxide and silver sulfide. No other secondary impurity peaks are present. Whereas in the case of indium doped silver sulfide and zinc oxide nanocomposite, a secondary impurity peak due to indium sulfide is present. The main reason is the activation energy of indium sulfide is very high, 0.88 electron volt. Compared to zinc oxide, it is only 0.34 electron volt. As a result, the nucleation rate is very rapid in the prescribed synthesized state. So more particles of indium sulfides are generated with a small reduced, say, as we can see, the width of the peak is very large. This shows a SAM micrograph of zinc oxide. It shows a flower-like arrangement. The petal widths are irregular with a range ranging from 400 nanometer to 700.
So, Dr. Rajeshwari, last 1 minute. So please try to summarize.
Silver sulfide and indium doped silver sulfide shows irregular spherical particles. When the dopant as well as the nanocomposites are formed, the flower-like morphology has been evolved to a one-dimensional rod-like structure. Whereas in indium, the rods are broken to pieces and the particles start adhering to the surface of the particle because of the Oswald ripening process. Here shows the optical property. If you see the absorptions property, the pure zinc oxide has the absorptions only in the UV region, whereas the composite ZAS and ZAIS have a high absorptions covering the entire region from 300 to 1100 nanometer, showing the broad focus, which is essential for solar cells. So here we have deposited the solar cells, ITO coated substrate. Over that we have the N-type nanocomposite and P-type rose Bengal. Gold electrodes are given as a thermal evaporated technique. So the overall thickness of the film is found to be around 120 nanometer. As they are chemically deposited by dip coating method and spin coating method, the single individual layer is not visible. So here comes the working. So if you see the rose Bengal, PN junctions is formed. So as indium is incorporated, it has an iron 3 plus extra electrons are present. It is just below the conduction band edge maximum of silver sulfide. So once the solar energy is forced on it, the electron from the valence band moves to the conduction and then facilitated to top and then over to zinc oxide. So multiple band transitions takes place without any loss in the recombination process. So this promotes the facile charge transfer. So when the efficiency is measured for the zinc oxide with the silver sulfide nanocomposites, the efficiency was found to be 0.76. Whereas in the case of indium doped silver, it is found to be 1.2%. Though it is a slight increment, we can see it becomes a very good for the future scope. So this
I think, is this the summary slides, madam?
Yes, sir. Next comes the summary.
Okay.
So because of the high conductivity and the nano size interface, the integrating these two properties have improved the efficiency to be 1.2% in the case of thing. So simple wet maker methods is used for light harvesting. Nano size confinement with the one-dimensional zinc rods, it's reduce the contact resistance, so in heterojunction. And indium doped silver sulfide sensitized have a higher efficiency of 1.2%, and this have a good control over PV parameters. Thank you all.
Okay. Thank you, madam. Thank you for very interesting talk.
Thank you,
very
sir.
good work. Yeah.
Thank
So if there are questions from the viewers, then we can take up.
Yeah, I want to ask you one question, that your efficiency is quite low, 1.2%. So
Yes,
did
sir.
you thought of some ways out to improve this number?
So if you see, still the current what we have measured is in the range of milliampere. It is not in the close to ampere range. So being a chemical depositions technique, the shunt resistance and series resistance which are present at the interfaces may be a barrier for the current to flow. So in our next studies, we are incorporating the same thing with the high improved structure. So that may be the reason for the reduced efficiency for the composite formations.
Okay, thank you so much, Dr.
Yes,
Rajeshwari.
Thank you, sir.
Okay.
Thank you all.
Good luck for the next research.
Thank
okay,
you,
so Dr. Tarun, we can have a next speaker, please.
Next speaker is Mr. Tamil Harasan, and the title of his presentation is Structural and Electronic Properties of AM02 ab initio. Mr. Tamil Harasan is there?
Yes, sir, I'm here.
Yeah.
Yes.
Yeah, we can see your screen. We can see your screen. So you can start now. Yeah.
Yes, thank you, sir. So I did a work on americium dioxide. It's basically an actinide oxide. Why we are interested about is it is moving or not?
Yes, slide is not changing, but I can try changing.
Okay, it's taking some time.
Yeah, now it's fine. Keep in presentation mode, please.
Yes, sir. Yes, sir. Yes. I'm from the Department of Physics and School of Advanced Sciences, Vellore Institute of Technology, VIT. And this work is guided by Dr. Arpan Kumar Nayak, sir. Yes. This actinide material is well known for breeder. Breeder means nuclear reactions. And why we are taking this problem is it's challenging for explaining the electronic and structural properties. And why it is so is because it has the 5 electron in it, and the hybridization is a little bit challenging to explain. And previously, some of the reports already reported that material is paramagnetic, which is the cited 9. This is an experimental work. So this is an experimental work, and some of other theoretical work which was based on hybrid DFT and FP Lapa LO is this LO is basically this is a spin orbital coupling only for F electron. These people also treated this AMO2, and why I am being is we are attracted by the mud insulator property in it. What is mud insulator? When you treat with the PBE, generalized gradient approximation, and localized density approximation, this is nothing but a classical model and a quantized model. If you're treating this will show us a metallic band structure. Okay, and this is the conduction band, and this is the valence band. In between, this is a Fermi level, let us assume. And if you, without going with spin, this is called as a it will show like this. And if you treat in a Hubert's model, this will show a band gap. In one spin, it will show a metallic nature. In another spin, it will show us a semiconducting nature or a insulating property. Most of the mud insulator will show a insulating property. And we have taken this unit cell. The unit cell is basically from FM3M, and it's along 2 to 5 in the space group number. And its Wyckoff positions of oxygen is 8C along 1, 2, 3 here. And this americium will occupy the 4A occupation. And then we have calculated the experiment. We have taken the experimental lattice parameter and the experimental crystal structure to this theoretical work. What we actually done is we just done the bulk modulus, because we want to found the ground state property, means a ground state structure. If this is means that we are treating the temperature inside the structure is 0, and pressure inside the crystal structure is along 1.7, which I did not put in the table, but it is here. And then we vary the volume up to some constant. We have taken the volume variation constant as 2, and what we will do is we just taken that experimental lattice parameter, then we will multiply from -4, -2, then multiply with 0. So 0 means the constant as b. Then again we will multiply with +2 and +4, then we will get the slope like this, sorry, straight line like this. And we have taken the particular area of the experimental lattice parameter. That's why we have got this much of straight line. And then we obtain the volume of the unit cell is about to 230.513 about Armstrong cube. And then we calculated that lattice parameter about 5.378, which is almost 0.5 on 0.3% of error in the other works and experimental work. And here we already took on that generalized gradient approximation for a exchange correlation to treat the bulk modulus of the crystal structure.
So you
Yes,
have
sir?
last 1 minute, so please summarize.
Okay, sir. So this is what we done with the generalized gradient approximation. We got the metallic band gap here, means overlapping of bands, and here also. And then this is the Hubert model. We use the U parameter. U parameter is nothing but the electronic exchange, sorry, Coulombic repulsion, and what Hubert's parameter is U, and J is the Coulombic repulsion. So U effective is 6 electron volt. That's why we got this separation in the 3.8 electron volt, which is referred from the previous theoretical works. And then here we can identify the hybridization of the sigma bond and pi bond belongs to the oxygen and americium. And mostly the oxygen atoms are aligned towards the AM atom. And then this is the density of plots for the GGA plus U model. And we found that 5 electrons are given trouble for the spin up, and there is no d orbital contribution in the spin down. Means that when we looking for the americium electronic configuration, it is as 6d as 0, and that's what it is showing is this is our degeneracy of other orbitals, and this is not the d orbital. And then this is the conclusion. We have performed the bulk modulus and the electronic state properties of the band gap is about 3.5 to 3.8 electron volts. It is being as a multi-insulator property has been verified, and the bond length has been calculated from the 2D electron contour. And then it also can be a breeder source and a breeder blanket. Breeder blanket means it can be able to control the reaction. Thank you. These are the reference. Thank you.
Okay, thank you so much. So let's see. Yeah, so Professor Asutosh, you have any question?
Yeah, right? Yeah, we would like to know which software did you use to simulate all this?
I was also
and the simulation.
I also wanted to know that.
Time and the machine.
Yes.
Quantum Espresso?
Yes. No. This is a licensed version of VN2K.
VIT has the license?
No. This is as physics department has the license.
Okay.
And I'm growing by your questions, so question opens to all.
So DFT has this problem, like you have to find the minimum energy configuration and lattice spacing. So did in the first slide you showed some comparison with the experimental values? Is that what you did for that?
Actually, we took on the lattice parameter of experimental people, what they worked for the their XRD. what experimental people will do is they will took nanoparticle synthesis or a crystal synthesis. They will do the XRD or powder XRD. Then they will, for if they've done the powder XRD, then they will go for a Rietveld analysis. Then they will find out the lattice parameter. That is our information we can took. That information is given to the input file as this bulk modulus here. So that one is the same one. Okay, sir. Then this is what we optimized. This is, we can say this as a accurate for theoretical works.
Yeah, but you
So
didn't show any variation. Did you show any variation? Okay, in this plot, okay, we cannot. Okay, so did you do any variation and found out the minimum energy?
Yes, sir. Actually, we started with this one. This has a one. We given the variation as 1%. Okay, sir. If we subtract to -2, then we get this one, this value. Okay, sir. Then if we increase to +2, then we will get this value. So this is this, and this is this. So this theoretical work is along here. We actually going for the accurate value, and this corresponding bulk modulus was calculated here and also here. And the pressure inside the system is this much, 1.184 gigapascal.
Okay. Okay. All right.
Okay.
Any other question from anyone?
Okay.
Okay. If not, okay. Thank you very much. Thank you.
Thank you.
Thank you, sir.
So Tarunji, you can have another speaker.
Yeah. Next speaker is Dr. Jayachandran J. And the title of the presentation is Investigation of Piezoelectric Microcantilever Coupled with Square-Shaped Micromembrane for an Energy Harvesting Application. Dr. Jayachandran?
Sir.
Yeah, you can share your screen, please.
Sir, is it visible?
Yeah, it is visible perfectly. You are perfectly audible as well. Can you put in presentation mode, please? Thank you. You can start.
Yeah, please start.
My research topic is investigation of piezoelectric microcantilever coupled with square-shaped membrane for an energy harvesting applications. My main objectives are to simulate and analyze the piezoelectric microcantilevers based energy harvesting system for the conversion of an external disturbance like pressure or force into an usable electric energy, to design the microcantilever coupled with square-shaped micromembrane with variable thickness for analyzing the mechanical behavior of the proposed system, and to analyze the energy harvesting performance of the piezoelectric material coated microcantilevers system, and to evaluate the optimized thickness of the membrane as well as microcantilever for gaining the maximum output potential, and to, finally to compare the simulation results and select the best one for fabrication. In introduction, energy is an integral part of essential source of our day-to-day life. Thereby, every activity is dependent on energy. Nowadays, the increasing of energy demand is one of the major issues owing to decreasing of conventional fossil fuels energy sources and environmental concerns. To overcome to this, energy harvesting is the technology to convert the naturally available and wasted energy into an usable electric energy. The main advantage of this energy harvesting technology is include the energy transition and recycling of energy from waste. It satisfies the requirement of low power energy based systems. The energy harvesting system consists of three major systems, which are energy recognition unit, energy transduction and power condition, and energy storage. Here the energy recognition is the input of an input unit to the energy transmission system. Then it converts the input energy into an equivalent electric energy. Then the power conditioning system controls the generated power and translate the energy storage unit. The energy storage units are like capacitors and batteries will be used. Based on the source of energy sources, we are classified into 3 types: natural source, temperature gradient, and relative motions. The natural source energy harvesting gives maximum amount of energy compared to the other 2 sources. Among this type of energy harvesting system, we are focusing on the piezoelectric energy harvesting for small device applications. Already we are familiar with the piezoelectric method, piezoelectric effects. There are 2 types of piezoelectric effects. One is direct and another one is indirect. Each effect are having 3 modes of operations called as longitudinal, transverse, and shear modes. These are some of the examples of piezoelectric materials. These are some of the piezoelectric material-based energy harvesting systems used for various applications like in this work, the piezoelectric cantilever are used to measure the air pressure and bridge vibrations and vehicle motions and human motions. And another one work is the piezoelectric material was placed into the rectangular shaped cantilever beam, and in this work they have created the rectangular cavities with single cavity and multiple cavities, and analyzed the energy harvesting performance of the material. And in this work, the membrane-based energy harvesting system was focused on this topic. In this work, the piezoelectric material was placed into the center of the membrane and analyzed the energy harvesting performance of the material. Here, the piezoelectric material cantilevers are utilized to find the air flow sensor. Based on these applications, what we thought is for coupling the membrane and with the piezoelectric micro cantilever will give maximum output, so that we are proposing the model is called the investigation with the piezoelectric micro cantilever coupled with square shaped membrane for energy harvesting applications. The proposed system having the as a square shaped fixed frame and 4 micro cantilevers which are coupled with square shaped micro membrane. These are the materials we are using: silicon as a frame, and VITC-2020 was used for piezoelectric material, and the gold electrodes were used as a charge collector, and membrane silicon membrane was used as a membrane for high mechanical stability. And the proposed method was executed for finite element analysis method, and the tool was selected for COMSOL multiphysics, which is specially designed for MEMS modules, MEMS devices, and in that the piezoelectric device interface was used for simulate this model. The cantilever structure consists of silicon as a base material. Over the silicon, the gold layer was coated and placed on the silicon. After that, the VITC-2020 material was placed, and after that, the
Dr. Jayachandran, you have last 1 minute, so please summarize.
Then the piezoelectric material was coupled with the square shaped membrane. The membrane acts as an input source. So when the pressure hits on the surface of the membrane will deflect the up and down. So the energy was transferred into the piezoelectric cantilever. The cantilever, based on this deflection, the cantilever gets strained. So the energy will be developed. This is the best view of the structure. This is the performance studies used for this work. This is the result. Initially, we applied the 200 Pascal to the system. It shows in the figure here shows the displacement V of the proposed system, and this is the Warner stress analysis of the system. This figure clearly shows the maximum stress distribution was occurred in the cantilever, each cantilevers, and this is the based on the stress experienced by the cantilever. This is the volumetric strain curves. This is the simulated view of the proposed system. While the membrane goes the ups and down, the moment creates the compressive strain to the cantilever structure, then based on the strain, the charge will be developed. This is the results for 1 micrometer thickness, and this is the results for 0.7 micrometer thickness. Here this is the results for 0.5 micrometer thickness, and the comparative analysis, the 0.5 micrometer thickness based system gives a linear displacement compared to other two systems. This is the Warner stress analysis of the proposed system. Here, all the three curves explains that the proposed system has a withstand capacity based on the applied pressure. This is the volumetric strain with the electric potential developed. Again, here also shows the 0.5 micrometer thickness gives the maximum, goes the maximum volumetric strain and gives the maximum output in the form of electric potential. In the conclusion, the piezoelectric material coupled with square-shaped membrane was simulated at the variable thickness such as 1 micrometer, 0.5 micrometer, and 0.75 micrometer, and studied the output performance. Each system, the energy harvesting system with 0.5 micrometer thickness square-shaped membrane generate a maximum output potential of 0.186 microvolt for the maximum applied pressure range of 200 Pascal, which is higher than the other two systems. The system with 0.5 micrometer membrane-based system could be taken for the fabrication, and it will be allowed for the real-time application after the detailed trial experimental investigations.
Okay. I think you can stop anyway. We can read the slides. So, Professor Asutosh, you want to ask question?
Yeah. One simple question to you. So you have said that 186 microvolts is the potential generated, but you want to harvest the energy. Then how much really the current your device can drive? Did you check that?
No, sir, not yet. This work was just started, sir.
Okay, because the energy is what? Power into time, and power is the potential multiplied by the current. So how much it can drive, that you should test with such a small, tiny size.
Yes, sir.
Okay.
Yeah. Okay, and I have a just simple suggestion that you can also, compare your results with the literature, already existing literature, so that
exactly.
you will have some idea.
Okay.
So since you are starting, so that will be a nice work. And if you compare, then you will have some parameters to tune with, and then improve your results, right?
Yes, sir.
So that was just a simple suggestion.
Yeah, particularly I feel like what's so special about your design, that how it distinguishes from the other work, or what advantage it has got, which you have simulated in COMSOL. So do you see any advantage of this design, or can you demonstrate the advantage of this design?
Yes, sir. The main advantage of this design is here the membrane. Membrane is one of the main advantages. While any external pressure variations acts on the membrane, so it will oscillate with ups and downs. So based on this ups and downs, each cantilever will get strained, sir. Based on the strain, the charges will be developed.
That's okay, but what we are saying that you can compare the amount of voltage generated by strain produced. You per percentage of strain produced by the existing literature, right? How the literature,
I will go
to understand. So whether you can compare, after comparing, you will know that whether your results are, in the, I mean, they are comparative. I mean, whether they are comparable or it requires further, improvisation. So
yes, sir. Yes, sir. I got it.
so that's the suggestion. Okay, so thank you so much.
Thank you.
Okay, so Dr. Tarun,
Yeah.
please, the next speaker, please.
Yeah, next speaker is Mr. Mavin Vincent, and
Hello, sir.
The title of his presentation is Pseudo-capacitive hybrid TiO2 cathodes for long-lasting magnesium-lithium dual-ion batteries. Over to Mr. Vincent.
Hello, sir. Thank you.
You're welcome.
So, Mr. Vincent, please share your screen.
Yeah, I'm doing. I'm audible?
Yeah, you are perfectly audible. We can see your slides as well.
Okay. Can I start now? Can I start?
Yeah, please go ahead. Please go ahead.
Okay, thank you. Thank you. Hi, everyone. Welcome to my presentation entitled Pseudo-capacitive hybrid TiO2 cathodes for long-lasting magnesium-lithium dual-ion batteries. Sorry, there is...
Can you exit presentation mode and yeah.
Yeah, I am. Sorry, sir. Just 1 second.
Yes, now it's fine.
Okay. You are seeing my screen, right?
Yes, we can see your screen.
Okay. Okay. So, yeah. Once again, welcome all to my presentation. The electrochemical storage is gaining so much prominence in the recent years in view of its better compatibility with the renewable resources to overcome the fossil fuel dependence. So far, the demand was mostly met with the lithium-ion batteries, but it cannot be a reliable source for the future because the lithium has a very limited abundance on the Earth crust, so the prices may be inflated or skyrocketed in the near future itself. In addition, the lithium always causes a dendrite drop once we are using lithium metal inside the battery. That always challenges the safety conditions. To overcome this, people have replaced lithium metal with some other metals like graphite, but on the cost of capacity, specific capacity. If you are replacing with the graphite, the specific capacity will fall down from the range of 2000 to 300. So people has to started think about the post-lithium technologies in which magnesium is one of the dominating. The advantage is it has a very high specific capacity that is almost twice, nearly 3,800 mAh per centimeter cube. And it has a very large abundance on the Earth crust, hence lower cost, and it is also an eco-friendly material. But in practical scale, a magnesium battery also experiences lots of some challenges. One of the main challenge is the divalent magnesium ion, once it is tried to intercalate to the cathode, the charge clouds on the cathode material will induce a repulsive electrostatic interaction that causes a sluggish ion intercalation, hence to poor electrochemical performances. To overcome this drawback of a pure magnesium battery, people have introduced the concept of a magnesium hybrid. The idea is magnesium electrolyte will be modified with a secondary ion. As of now, it may be either lithium or sodium. Can also try other materials, so that the charge storage on the cathode side will be dominated with this secondary ion. In practical scale, the challenges for a magnesium hybrid battery is developing a dual ion containing electrolyte. Also, a cathode which is compatible to both ions is a challenging work. Here in my work, I'm trying the possibility of magnesium TiO2 electrodes as a feasible magnesium lithium electrodes. For that, have synthesized TiO2 nanosheets using the hydrothermal method. The as prepared material was pure bronze, which is then turned into bronze anatase hybrid and to pure anatase by changing the calcination temperatures. The prepared materials were subjected for the chemical composition analysis with XRD and by means of Raman. The as prepared materials found to be pure bronze with no other extra peaks, both in XRD and Raman. But with increasing the calcination temperature, anatase phase also start to appear. And the calcination at intermediate temperatures gives anatase bronze hybrid, and a high temperature calcination at 500 turns the material into pure anatase. A relative comparison of anatase bronze peak in the XRD as well as in Raman gives a relative ratio of 60:40 anatase bronze ratio in TiO2 AB1 hybrid and 90:10 anatase bronze ratio in TiO2 AB2 hybrid. Further, the morphology of these materials, TiO2 were investigated with TEM. It shows a nanosheet structure. The advantage of nanosheet is it gives a better contact surface between the electrode and electrolyte and hence to better electrochemical performances. Also, all these nanosheets were aggregated in the form of spherical clusters. The spherical cluster morphology is advantageous in resisting the electrode polarization under electrochemical cycling. The high resolution images shows two lattice spacing corresponding to both anatase and bronze, which is confirming the hybrid nature of the electrodes. The synthesized materials were made into electrodes and used to make magnesium lithium hybrid batteries and then subjected to electrochemical analysis. The first figure shows the galvanostatic rate performance of the batteries with having different electrode materials. The TiO2 AB1 electrode, the AB1 hybrid shows the best performance. At 25 milliampere, it shows a specific capacity of nearly 230 mAh per gram, and at 1 ampere, it retained a specific capacity of nearly 120 mAh. Its performance was dominant to all the other three electrodes. The second figure shows the second cycle voltage profile of the AB1 electrode at different current densities ranging from 25 milliampere to 1 ampere. One characteristic is all these patterns follows a sloping nature. The sloping nature is a significant fingerprint nature of a capacitive type charge storage, which is advantageous for having better capacities or storage capacities. Following the electrochemical analysis, the first figure shows the cycling performance of the AB1 electrode. The batteries were stable up to nearly 3,000 cycles.
Maybe you have a last 1 minute. So
okay, 3,000 cycles, which means the stability. It shows the stability of the electrode. Further, for understanding the storage mechanism, we subjected for the cyclic voltammetric studies. The log scale between the peak current and the sweep rate shows curves for anodic and cathodic lines with a slope rate of 0.75, which is demonstrating a capacitive type charge storage. Further, we qualitatively segregated the capacitive and diffusion contribution. It shows a very always a dominant capacitive performance of the AB1 electrode. It reaches nearly 92% at 10 millivolt, which is very high for magnesium-based materials. For further understanding the real mechanism taking place on the electrode, we subject this electrode for the Xc to XRD analysis. It shows the anatase peaks remains stable throughout the voltage instance, whereas the bronze phase cyclically undergone an amorphization, which we are observed at 0 and 1 volt here. This shows capacitive type charge storage taking place in the electrode. The mechanism can be better understood in the schematic. The pure crystalline is changing to a bronze, amorphous bronze with discharge. So in conclusion, The AB1 hybrid with 60:40 anodized bronze showed a drastic improvement of the single-phase TiO2 and other hybrid cathodes. The electrode exhibited outstanding specific capacities, rate performance, and cycling stabilities. Also, the AB1 hybrid electrodes exhibited pseudo-capacitive type charge storage, which is the reason for its dominant performance. The magnesium lithium hybrid system outperformed the magnesium battery in terms of specific capacity, rate performance, and cycling stabilities. And thanking you all for your attention, and I'm ready to answer if you have any doubts. Thank you.
Okay, very nice presentation, Mevin. So,
thank you, sir.
So viewers, if you have any questions, then please ask. Okay,
hello?
So is someone asking any?
Yeah, but it is not audible. It's not clear.
Okay, so I think if it is posted on the chat, please post on the chat. I will ask the questions to the speaker. If anyone is having any question, please post in the chat box. I will read for you, and then he will answer for you. Okay, so I think okay, I have one very small question.
Okay.
Do you have any comparative study between the lithium-ion battery and then the magnesium, the one that you are trying to do?
Okay.
Do you have any comparative data?
I don't have a real data to compare now, but in the practical, if you are comparing the practical magnesium and the magnesium lithium battery, the lithium performance is too high because the lithium batteries have been studied for maybe decades of years and it's already commercialized. A magnesium alternative is a newly emerging system. And actually the pure magnesium has lots of limitations and people couldn't achieve very high performances. That's why they are introducing this magnesium hybrids. So if you are checking the literature, there may be a maximum of 30 to 40 publications, which is dealing with the lithium magnesium hybrids. That itself shows the early stage of the technology. So
okay. So I think one viewer has a question.
Okay.
The question is, how do you control the phase of the TiO2, as it exists in many phases, right? So how can you control the phases?
It is easy. There are plenty of publications which is describing the methods. It is actually a hydrothermal system. So if you are changing the temperature, pressure, or the precursors we are using, or the other reaction environment creation, with all these things, we can easily synthesize the specific phase which we want. If you are checking, there are plenty of, and I just took one method which I found in the literature. I didn't do anything new for the synthesis.
Okay. So thank you so much, Mevin.
Okay, thank you.
Yeah. Okay, so I'll go to the next speaker.
Okay.
Tarun.
Yeah, sure. Yep. So Mr. Vinod, I guess this speaker is not available. So we'll be going to the next presentation, and the presenter name is Ms. Ravneet Kaur, and she will be talking on electron acceleration in cylindrical plasma. Ms. Ravneet Kaur. Is there? I can. Ms. Ravneet Kaur, can you please respond?
Hello, very good evening to one and all present over there.
Yeah, you can share your screen, please. Yeah, we can see your screen and we can hear you clearly. So please go ahead with your presentation.
So basically, I'll be talking about electron acceleration in cylindrical plasmas. This is completely theoretical studies under the supervision of Professor Nitikant, Dr. Jyoti Rajput, and the co-supervisor, Dr. Umberto Cabrera, is from the Abdus Salam International Center for Theoretical Physics, Trieste, Italy. And Basically, the outline of my presentation will be like abstract introduction, derivation, expected results, and the references. Theoretical investigation of the phenomena of electron acceleration by radially polarized laser is done in the cylindrical plasmas, and the expected results are that we can accelerate the electron up to some giga electron volts with the help of this laser, and the external magnetic field is applied through these helical undulators.
Excuse me,
And
Ravneet, excuse me. Can you keep your mic slightly away from your mouth so that we could hear you clearly?
So talking about the introduction, high energy particle accelerators are the most versatile, fascinating, exotic invention of the 20th century, which have led to the invaluable contribution toward the advancement and profound understanding of the things happening around us. Basically, this idea was put forward by Sir Isaac, and in 1979, the lasers were actually used to accelerate the electrons in plasmas. Studies are done in vacuum as well. Rapid response of electron present in the plasmas. The electric field of the laser pulse which we are using brings such interesting phenomena of the generation of high energy electrons. Basically, we are focusing on direct laser acceleration. We are having plasma wake field accelerations and other accelerators also, but our study is related to direct laser acceleration, in which the self-produced magnetic field in the plasma assists the electron acceleration. The Betatron oscillations are experienced by the electron when the magnetic field generated by the flow of accelerated electrons. The Doppler shift laser frequency is equal to the frequency of the oscillations of the electrons, and hence there is a transfer the energy from the laser part to the electron. The primary prerequisite is what the self-focusing of the laser, and as a result, if that is possible, then we can have accelerated electrons at the end. So this is the hello.
Yeah, we can hear you. We can hear you. We can see your screen as well.
So basically, these are the field equations. As I have mentioned, we are doing the theoretical work. So this is the main equation which we have taken for the laser, and the two components of the laser we have taken as ER and EZ. And furthermore, these are the results which are actually talking about the momentum of the electron, which the electrons which are accelerated. Basically, in this part, I would like to say that the presence of the azimuthal magnetic field improves the electron acceleration by keeping the electron motion parallel to the direction for longer distances, you can say. And the resonant occurs when we use the chirp laser pulse and the azimuthal magnetic field. So we can say that an electron with few mega electron volt of initial energy can have at the output, it can have giga electron volts of the energy. So this is a very small part of the work we have done, and furthermore we will be talking about the optimized values which we'll be doing through some simulation work, and so that we can have the electron in the giga electron volt range. And the main part of this research will be that these accelerated electrons can be used in particle physics application. Along with that, it is seen experimentally in number of European countries that these accelerated electrons can generate, furthermore, generate terahertz radiations, which are going to replace, which have already replaced the X-rays. Furthermore, these X-rays, those are very, very dangerous for human body. If they will be replaced with the help of terahertz, and terahertz can be generated from electrons, which are derived from this DLA. So that's all. These are the references, and thank you very much.
Thank you very much for presentation. Nice presentation. So, any question from the viewers? We have quite like 2-3 minutes of time.
Can you explain how did you get? I mean, how can you get say giga GeV kind of energy from the laser acceleration, and what?
Yes,
I mean,
sir.
anything. How can you get such high energy? Just
Yes. Basically, sir, as I said, we have derived these relations, and furthermore, what we will be doing, in the derived formulas, we'll be putting the values in the software, and then we can have. It is kind of simulation work. Like we'll be using some parameters from the literature survey. For example, the laser intensity will be taking of 10 to the power 19 watt per centimeter square, and the laser spot size will be chosen, and it is believed that
you just showed the equation. You didn't show any simulation results or any
yes
explanation.
Yes, because this is the only first part. After this, we will be doing the simulation part. These are the energy momentum equations. The second part is, in these equations we are going to we will be going for the numerical analysis.
Yeah, that is the future work, right? But you are when you are presenting, like you can get this equation from any textbook, right? So what
no, these are not from any textbook. These are the my derived results, which basically we have used the Praxial approach theory, in which the basic equations which I have showed of the electric field we take, and then we solve using the Maxwell's equation. We externally apply some azimuthal magnetic field, and further we derive the equations which are there for electron momentum and energies.
Okay, all right.
Okay. So thank you so much, Ravneet.
Okay, sir. Fine, sir. This is Madheswaran.
Yes, sir.
Dr. Tarun will join shortly.
Okay, sir.
I'll call next speaker, Dr. Bhavya.
Okay, sir.
Dr. Bhavya, could you please?
Yes, sir. I'm here.
Yeah, please share your presentation and start your presentation.
Yeah, sure. Thank you. Yeah, so good evening, one and all present over here. I'm very pleased to be part of this new normal where virtual conferences we are attending nowadays. And I'm from Newhausen College of Engineering, Dr. Bhavya P, working as senior assistant professor. And today my discussion topic, what I'm going to take up is quantum computational investigation. And this we are doing it for one of a heterocyclic organic compound called coumarin derivative. So I hope I have started my discussion. I'm audible to all of you.
Yes, please proceed.
Yes, you are audible. Yeah, pretty much audible.
Yeah, thank you. So coming to the presentation of today, these are the steps what I'm going to follow. Just a brief introduction we are going to have regarding the compound and all the technicals what we have used for the today's study, and then little bit materials and the instrumentation requirements also. Since it is a computational studies, it's basically the softwares what we have used that I'll be little bit I'm going to introduce. Then the experimental details, results and discussions, and finally the conclusions what I'm going to what we have derived from this study that I'm going to discuss here. Okay, so coming to the today's compound, actually, basically our studies is related to fluorescence, what we do here. And all the fluorescent compounds we study. And as we know that all the experimental studies, basically they are more supported by the theoretical investigations also. That is what in this small brief study we have tried to do, where all our fluorescent compounds, whatever we are going to study for the fluorescent spectroscopic behavior, for that we have supported some of the theoretical concepts. So only the theoretical concepts, whatever we have supported for our compounds, I'll be discussing in today's presentation. And these are different fluorophores what we use in our studies. And today's our discussion is mainly based on the coumarins. And the coumarins, this is the basic properties. They are actually laser dyes who give the emission spectra near blue and green spectral region. And the Stokes shifts and its dipole moment, these are some of the basic properties which are required, where further fluorescence quenching studies we will be doing for these compounds. So now, and also coumarin derivatives, when it comes to the application part, these are all some of the specialities what we see here. Medically, they are very highly relevant. That's why we call it as biological compounds also, because we use them for anti-tumor, antiviral, and different biological applications. And hence, these coumarins are very important compounds to be analyzed. That is what we have taken up. And coming to the quantum chemical computation, these are all computational techniques what we have used for the theoretical studies of a compound. And in today's presentation, these are the points what I'm going to discuss. So here we have, these are the studies basically what we have done. Electron dipole moment we have calculated theoretically. Homolumo analysis we have done. Molecular electrostatic potential has been studied. Mulkin atomic charges analysis we have done. NBO and NLO analysis also we have carried out through this quantum computational methods. And this is the basic flow chart, how a program runs for quantum computational studies here. As you can see from the flow chart, but with all the analysis and also the assumptions, whatever we do, finally at the end for the to go with the studies, optimization of the diagram or the compound is very, very important. So the further studies will start from optimization. That is also what we have done in our studies, optimization of the molecule, and then further all the other analysis, whatever I have mentioned in the earlier slide. Okay, so this is the derivative what we have used. In short, we call it as 3HBCD in the studies, and this is the molecular structure of the derivative. And coming to the coming to the computational details, DFT studies basically we have done, and basis set for coumarin derivative we have used 6311, and NBO version, NBO analysis, whatever we have done for that version is taken as 6.1. So that version we have used for arriving at the computational results. Okay, so now when we are talking about this computational studies, there are two kinds of analysis what we will do. One is each molecule, atom, whatever the wave functions they show. So approximate the wave functions using the Schrodinger's wave equation, and then arrive at the total picture of the molecule. That is one way of analysis, which is more and more complicated. And another way of analysis, what basically we can use is using the electron density function. So electron density, wherever it is more, that we will analyze, and then we will finalize the molecular structure. And to do this quantum mechanics, quantum computational studies, there are different methodologies available. Ab initio method, basically, which, as I mentioned you, it uses Schrodinger's equation to approximate the wave functions, and semi-empirical method, that is also slightly deviated towards Schrodinger's wave equation only. And our studies, what we have used is density functional theory. So here I have mentioned that ab initio method wave function approximation requires more of mathematical analysis, more complicated. And our studies, DFT studies, is more simple because price-wise also, the software and analysis price-wise also, it is comfortable to afford. And also when we are talking about very large molecules, So wave function approximation becomes more and more complicated. So electron density approximation is more comfortable for large molecules. And hence we have preferred density functional theory for our studies, our coumarin being a very large molecule here with a good structure. And as I mentioned earlier, geometric optimization is the first step of what we have to do in our studies. And this is what the geometry optimization for 3HBCD we see here. The first diagram is about geometry optimization, and the second diagram, what you are seeing towards the right side, that is the dipole moment direction. As I stated earlier, we do fluorescence quenching studies, and fluorescence quenching studies basically we carry out in different organic solvents. And when we dissolve these compounds in organic solvents, their interaction with the solvents matters a lot. And that kind of analysis before in hand, the experimentation we can do by analyzing the dipole moment of the molecule. And this is the theoretical dipole moment calculation what we have done along with its direction. Okay, so next what study we have done is frontier orbital characterization, FMO studies we call it, where it will tell you the charge concentration in the higher occupied orbital and lower unoccupied orbital. So that in short we call it as HOMO-LUMO studies. And according to the HOMO-LUMO studies, what we have done, you can observe that in the lower energy level, highest occupied energy level, charge density is more observed in isatin ring. Actually, this particular part were, I hope my cursor is visible to all of you.
Yes, Dr. Babia, yeah, it's visible. You have last 1 minute, so I think you can summarize.
Oh, okay, so never realized, sorry for that.
No problem. Yes.
Yeah, so this is about the HOMO-LUMO studies. Then I'll just go through the diagrams and I'll highlight the observations what we have done. And here we see that isatin ring, coumarin ring, there is a charge transfer happening when the molecules are excited from HOMO to LUMO. And this is Mulkin atomic charges studies what we have done, and red to green, this is where the potential of the molecule will be analyzed. But in our 3HBCD, as we observe, around oxygen atom there is a little red region for high potential, and or otherwise it's in a light green color, which tells that our compound is most of a neutral potential compound rather than two extremities of low potential and high potential. Okay, so then we have studied NBO also, and NBO analysis is very much important to analyze how these compounds are going to interact with the organic solvent molecule. So intramolecular and intermolecular bonding, what they form, what are the possibilities that we have studied, and where we have shown that probable transitions, so numbering of the compounds were there in the earlier slides. So these are all the possible intermolecular and intramolecular bonding what we can see. Okay, I've come to my conclusions now. And NLO studies also we have done, and NLO studies basically we compare with the standard compound and we do the studies. Non-linear optical properties we call them. And here we have used urea for the comparison. And according to the comparison, this 3HBCD, whatever we have studied, it is 1.6 times NLO active than the urea, whatever the compare. So that will tell you for NLO properties how much we can prefer these compounds. And according to my all other compounds, whatever we have studied, coumarin derivatives, basically they show better NLO activity. Okay, so conclusions wise, coumarin derivatives, they have good stability and strength. When we optimize the diagram, these are the other parameters also what we study. Potential and the chemical hardness, chemical softness and all. According to that study, chemical stability is good for the coumarin derivative, and MEP analysis predominantly, as I told you, neutral potential, the green color and the blue region. And the charge transfer is happening between coumarin ring to isatin ring, and 3HBCD is a better heterocyclic molecule for NLO studies also. So I think with this, I have concluded my presentation, and these are all my research associates with whom we are carrying out these studies. And thank you for this great opportunity to be part of the conference and helping me to present my work in a short and brief way. Yeah,
okay, thank you so much, Bhabya, Dr. Bhabya, for presenting your result. The viewers have asked, one viewer has asked one question. So
Yes.
this is time. If you are ready, then we can ask, we can start question. Okay, so
so hybrid basis. So hybrid basis
no,
sets
no,
why we have.
So the question is why the hybrid basis set rather than the PWC and PWE? Because he suggests that he thinks that the computationally PB required less time. That was the question.
Basically, when we were doing this computation and analysis, different basis sets we utilized, and since molecule being very much larger, different the lower version of basis sets only they were unable to give the result, and we had kept these computations for weeks together where we couldn't get the output, and finally we ended up with this particular basis set where I think we took around 1 week to extract all these results from the computational studies. So all trial errors were done, and then this basis set was finalized based on the time limits and also the feasibility of like obtaining the results.
Okay. So, I have one question.
Yes, sir.
Why did you choose? Why organic compounds? You can have. There are many inorganic compounds as well, right? They are very good fluorescent molecule.
Yes, so basically here we prefer organic compounds because they are biologically very like nature friendly also.
Okay.
And also planning for applications later, sensing applications and other applications. Biologically friendly molecules are more preferred than inorganic compounds. So we have gone for these organic compounds which are biologically friendly.
Okay. Okay. So thank you for your answer.
Yeah.
Okay, so sir, Madhasuran sir, we can have a, next speaker. I think we don't have any other question.
Sorry, no questions from Dr. Asutosh?
No. Thank you. Nice presentation.
Okay. So next presenter is Mr. Kanagavel.
Hello, sir. Good evening.
Could you please share your slide?
Am I audible,
Start
sir?
your present. Yeah, you are audible.
Yeah. Okay. Just 1 second, sir. Sir, is my presentation window is visible to all of you?
Yes, it's visible. Yeah, please go ahead.
Thank you very much, sir, for the opportunity. Myself, Kanagavil, I'm doing a research under Dr. James Jabasilan, sir, in VIT Vellore in part-time. So my topic is dosimetric evaluation of a newly launched commercial detector, radiation detector in triple F beam, that is flattening filter free beam, and comparison with different detectors already studied, worldwide. These are all some outlines. So introduction, objectives, and materials and methods and all. So as this study is being done at radiotherapy linear accelerator machine. So as per the radiotherapy, the goal is delivering high dose to tumor to eradicate the tumor, and at the same time you have to give a very low dose, that is nothing but an X-ray radiation dose to the normal structures. That is the aim of the radiotherapy. And here we have chosen the linear accelerator with one particular vendor called Electa. So it has so many high-end imaging system and high energy X-ray machines having different voltage, which I will be explaining in coming slides. So after installation, if you ask us, we can go for the treatment. No, we cannot go for the treatment because you need to do some validation. So what kind of validation is nothing but you have to characterize your beam, and that beam characterization should be modeled in your treatment planning system. So for doing that characterization, we need certain equipments, which we used to call as radiation therapy detectors and associated phantom materials. So your quality of the beam data, which gives very accurate dose to the patients. So both are interrelated. Without good data, we can't deliver the very good accurate dose to the patients, because we are using X-rays. We need to spare normal tissues as well. At the same time, we need to do high dose to the tumor. So in this case, dosimetry is very important. So dosimetry is something nothing but just measuring in water using some radiation dosimeter based on the some material, water material, and kind of a electrometer. So once dosimetry somehow it should be. So what are the protocols we are following? So there is one international protocol which is IEC 60731, which talks about how one dosimetry system should be, and some other international protocol which is IAEA protocol number 3 TRS 398, how the dose should be. And when you go for a very special technique, very small tumor treatment, how the your beam data should be. So these are all the protocols talks about all those stuffs. But in this study, we have taken a new chamber introduced by a company called the PTW, which is the chamber ionization chamber. We call it as semi-flex 3D chamber. This we wanted to study under this linear accelerator how characterized dosimetrically based on the protocols, and we took some references already published for different detectors. So comparing with that, how this detector is performing. This is the objective. So the first here we have taken into two parts. One is how one ideal dosimeter should be is based on these characteristics: sensitivity, linearity, dose state dependency under the machine in X-ray beam, and different energy if I use a particular detector, how it will react for it, and what is the reproducibility and all. And not only that, you need to have another measurements, beam measurements, which is percentage depth dose, beam profile measurements, and output factor measurements. So combining two measurements, we took that particular detector for both the measurements, and finally we compared with the different detectors available in the literature. So in that way, we chosen that Electra machine, which is Varsha HT model, high-end machines, which has both flattening filter and flattening filter free photon beams, and high electron volt electron beams as well. The maximum dose rate, it has 2400 MU per minute, by which one can one patient can get the radiation very quickly, and then they can go for the rest. So what is the difference between double F and triple F? Nothing but only one flattening filter. You can look at this picture. In the first picture, there is a cone type filter which attenuate your cone beam X-ray beam after the target, which will make as a flattened beam. But in this case, it has some disadvantages. Your normal structures will have some higher dose compared to unflattened beam. So in unflattened beam, without filter, your raw beam is coming. So only tumor will have higher radiation, and normal structures will have very less radiation. That's the advantage of triple F beam. So under this particular beam, how our detector is going to be. Then for doing the measurements, we took an automatic water tank system, which is PTW MP3M water tank system, which has the dimensions of this, and along with this some electrometer. These are all the detector which I have taken for the studies. The semi-flux 3D, the red one is the to be studied and compared with other detectors, pinpoint and diode P, diode E. This is shielded diode, this is unshielded diode, and semi-flux chamber almost near to this, but there is a conventional one, and micro diamond detector. It's a kind of a synthetic diamond detector. So all this has its own characteristics. So all the detectors is characterized based on the volume of the material. So all ionization chambers are having air volume vented, air volume ionization chamber, and diode detectors are silicon material, and diamond detector is having carbon synthetic diamond detector. So these are all operated at different voltages. So and another important is that how the procedure. So we have taken two measurement setup. One is for characterizing the sensitivity, reproducibility. This is the setup.
So last 1 minute.
Yes, sir.
So please summarize. Yeah.
Yes, sir. And these are all the setup for, for measurements. So sensitivity for both of the detector is very comparable with, other detectors, and linearity is also very comparable, very linearly according to the dose. Charges are getting increased. Energy also is very independent compared to other detectors, and dose rate dependency also very stable, which means at any dose rate you can use it. And when it comes to percentage depth dose, only very small field size, it has some difference. This is being decreasing when you increase the field sizes. So that is being observed in the study. And we compared this profile as well. In this profile, there is a problem in the very small field, which is called volume averaging effect. So it will underestimate at the central axis of the beam and overestimate at the penumbral area. So that has been avoided in this, when you go for 1:1 field size, very small field size. But if you go with very high field size, this effect is now, which means the detector can be used, from only 3:3 to larger field size. Maximum field size is 40/40. And when it comes to output factor for the larger field size, the studied detector is very comparable with other ionization chamber. Whereas with small field, there is a deviation, which is because of volume averaging effect. So as a conclusion, the semiflex 3D chamber can be used for nominal field size, which is from 3:3 to 40/40. If you go down to that, there will be a volume averaging effect. So this is my acknowledgement for the study, and these are some references. Thank you.
Okay, so thank you so much for a very nice presentation.
Yes.
Nice work, and I hope this will have some real life application, right?
Yes, sir.
This is for real life application. So, okay, so let's see the viewers. Professor Asutosh, you have question?
Yeah, I have one question.
Yes, sir.
See, you have this FF and FFF, two types of beam patterns, right?
Yes.
And
Yes,
then
sir.
you talked about the various detectors.
Yes.
So can you go to your plot which you showed us?
So
Yes,
there are so many
in the
plots.
result, you compared different detectors. You compared for.
This is the one.
Yeah, I think slide number 22, 21 and 22.
Okay, 1 second.
21 and 22.
Yeah, this is 22. Yeah, this is 21. Yeah. Is it the one you wanted?
Yeah. Yeah. This is the one. So now what you see, your detectors is so it's not clear. Is the size changing with this of the detector, and that is why you are having different pattern for different
Yes. See what I have taken.
or is the size different?
Yes, sir. Actually, there is another detector also is there, which is being already studied as per the international protocol, which is called semiflex chamber. It has 0.125 cc volume, air volume. So I took as for sensitivity study, I took this particular chamber as a reference, and I normalize my data to that particular detector. So if I take the semiflex chamber data is 1, my factor, and how much variation to my studied detector, which is semiflex 3D, which is almost very near to 1. You can say, which compared to other detectors, this is very near to my reference detector. This is for double of beam. Whereas when you go
But
for
the confusion, like you ideally would.
Yes, sir, please.
You would like to keep your detector as very small, no? I mean, as small. If it is a diode detector, they can have pretty small surface area.
Yes.
So
yes.
how does the comparison between? Why are you comparing them with this double F and triple F beams? I mean, if the area is really small, then the beam variation should not affect the detector performance, isn't it?
No, sir. It is not the, it's the same field size I have maintained here, which means beam opening is same for all the studies, and especially for the characterization. So here why I have taken is, I just thought of studying this, both the double F and triple F, how my detector is performing. So in both the way, my detector is almost stable, except for triple F, very low MU, I have very low sensitivity because volume is less compared to other detectors, especially the reference detector. So that's what the conclusion I wanted to specify in this particular sensitivity property. Similarly, if you go with linearity, depends on the volume, your linearity curves is getting changed.
Okay, can you just tell us the ratio of your beam size and your detector size? Roughly, what is the ratio of the beam area and typically the width, whatever you showed in the
See, my detector size is, I can show you here. This is my detector size. The volume is, 0.07 cc, which means very small. This is my maximum size. But my opening width will be almost, 10 centimeter by 10 centimeter. Because I need to cover the full area. And 10 by 10 is my reference field for my linear accelerator, where my linear accelerator is tuned to deliver. For example, if you deliver 100 mu, you will get the 100 centigrade dose, radiation dose to the patient. So I took that particular field size as a reference. That's why that field size has been taken.
No, but the active area is small, right?
This for chamber active area is very small. Yes.
Okay.
Okay, all right. Thank you very much.
Thank you. Thank you very much for nice presentation.
Yes, sir. Thank you.
Okay, so Professor Madheswaran, Tarun.
Yeah. So thank you, Dr. Lakshminarayan Tripathi.
Thank you so much.
Thank you, Dr. Ashutosh, for sparing your valuable time. So I am thanking you on behalf of the organizing committee of VITC 2020.
You're most welcome.
Thank you very much, sir.
So thank you, Professor Lakshminarayan.
Thank you, sir. Yeah.
Thank
you very much.
Have a good night.
Okay, thank you, sir.
Okay, thank you all. Thank you.
Thank you, sir.
Yeah.
Okay, dear participant, the session is over now. Please join tomorrow morning session at 9 a.m. Now you can sign off.
நானும் க்ளோஸ் பண்ணிக்கலாமா?
Okay, sir. Bye, sir. Bye, sir.
இல்ல இங்கதான் இருக்கேன். ரெக்கார்ட் ஆஃப் பண்ணுங்க. யூடியூப் லைவ் ஸ்ட்ரீம் ஸ்டாப் பண்ணிட்டு அப்புறம் எண்ட் கொடுங்க.
Okay, sir. Fine.
First recording close, then YouTube close, then sign off.
Okay, fine.
Leave all choose பண்ணிங்க. ரெக்கார்டிங் போட்டுக்கலாம், பக்கத்துல ஸ்டாப் இருக்கும் பாருங்க. யூடியூபும் கட் பண்ணிங்க.